Hello there, and welcome to Physics with William, where curiosity gets plenty of room, complicated ideas are allowed to slow down, and physics is explored without any expectation that you should be taking notes under the blanket. Tonight we are looking at something so familiar that it barely feels like a scientific idea at all. Cause and effect. You press a switch and the light comes on. You drop a spoon and it falls toward the floor. You leave a cup of tea untouched for long enough and it becomes disappointingly cold. One event happens, another follows, and the connection between them seems obvious. The cause comes first, the effect comes later. This simple order is built into almost everything we do, from making breakfast to explaining why stars shine. Yet modern physics has given us reasons to ask whether this arrangement is truly written into reality at its deepest level. Perhaps cause and effect are not the foundation beneath everything else. Perhaps they are something that appears only when the underlying world becomes large, stable, and familiar enough to resemble the one we experience every day. Before we go any further, think for a moment about what caused you to be here listening to this. Perhaps you saw the title and became curious. Perhaps you were already watching something about quantum mechanics and this appeared next. Perhaps you were looking for something quiet enough to fall asleep to without waking several hours later to discover that someone has been explaining black holes directly into your dreams. Whatever the reason, you can probably construct a chain of events that brought you here. Something happened, which influenced something else, which eventually led to this moment. That is how naturally the mind thinks in causes. We rarely notice ourselves doing it because the habit is almost automatic. If you enjoy these slow explorations of physics, you are very welcome to like the video and subscribe. That small action helps other curious listeners find the channel, giving us a perfectly ordinary example of one event affecting another before we begin questioning whether that comfortable picture survives all the way down to the foundations of nature. Cause and effect are useful because they give events an order. Imagine that you walk into the kitchen and find a broken glass on the floor. Your first instinct is not usually to accept the broken glass as a completely isolated fact. You wonder what happened. Perhaps someone knocked it from the counter. Perhaps the cat made another questionable decision. Perhaps it slipped from a wet hand. Whatever explanation you choose, you assume there is an earlier event connected to the later one. The glass did not shatter and then cause itself to be dropped. The broken pieces are evidence of something that happened before. This type of reasoning is so deeply connected to ordinary experience that reversing it sounds absurd. If somebody told you that the puddle on the pavement caused yesterday's rain, you would probably suspect they needed either more sleep or a different relationship with weather forecasting. Our world appears to be organized in a direction. Causes leave consequences. Earlier conditions shape later ones. The past seems to provide explanations for the present, while the future remains something that has not yet produced its evidence. Science grew very naturally out of this way of thinking. When we ask why an object moves, why a chemical reaction begins, why a disease spreads, or why a planet follows a particular path, we search for conditions that can explain what comes afterward. Classical physics made this especially powerful. If you know where an object is, how it is moving, and what forces are acting on it, you can often predict what it will do next. A ball rolls because it was pushed. A pendulum swings because gravity and its previous motion carry it through a repeating path. A planet changes direction because gravity affects its motion. The details can become complicated, but the logic remains reassuringly simple. The present contains information that allows us to calculate the future. For centuries, this picture worked so well that it was tempting to imagine the entire universe as a vast machine, with every event following from the events before it. Given enough information, perhaps everything could in principle be traced backward to its causes and forward to its consequences. That picture is not completely wrong. In fact, it is extraordinarily useful. The trouble begins when we assume that because something works perfectly at one scale, it must describe reality in exactly the same way at every scale. Physics has repeatedly warned us against that assumption. A solid table feels continuous, but on smaller scales it is made of atoms and enormous amounts of empty space. Temperature feels like a basic property of an object, but it becomes meaningful through the collective behavior of huge numbers of particles. A wave crossing the ocean looks like a single moving thing, even though the individual water molecules mostly move around their local positions. The large-scale world contains properties that are real and measurable, but do not necessarily exist in the same form at the microscopic level. This is what physicists mean when they talk about emergence. Something can be completely real without being fundamental. The possibility we are exploring is that causality may belong in that category. At first, this suggestion seems almost impossible to picture. If cause and effect are not fundamental, what could be underneath them? Surely something still has to happen first. Surely one thing must still produce another. But notice how quickly those questions already assume the very structure we are trying to examine. We are asking what caused causality to emerge, which is rather like asking what temperature a single isolated temperature is. The language itself begins to fight us. Human thought is built around sequences. We experience one moment and then another. We remember what happened earlier. We make decisions based on what we expect later. Our nervous systems are constantly learning which events predict other events. A sound from the kitchen may mean something has fallen. Dark clouds may mean rain is coming. A particular expression on someone's face may suggest that now is not the ideal moment to mention the broken glass. Cause and effect are not merely ideas from physics. They are part of how living creatures navigate the world. There is also a very practical reason for trusting causality. It works. If you place your hand close to a hot surface, you have good reason to expect discomfort. If you water a plant regularly, you can influence whether it survives. If engineers alter the shape of an aircraft wing, they can test how the change affects its behavior. Our ability to manipulate the world depends on reliable connections between actions and outcomes. Nothing about modern physics removes this. Even if causality turns out to be emergent at the deepest level, you will not wake tomorrow to discover that kettles boil before they are switched on. Large objects interact with their environments in ways that make ordinary causal order extremely stable. The idea that causality might emerge is therefore not a claim that everyday reality is unreliable. It is a question about why everyday reality is so reliable in the first place, and whether the rules we experience are the same rules that nature uses at every possible level. One of the first hints that our ordinary assumptions might be too simple came from relativity. Before relativity, it was natural to imagine that the universe possessed one universal time. Events happened in a single shared order, and every observer, at least in principle, could agree about what was happening now. Relativity changed that. Observers moving differently can disagree about how much time passes between events. For sufficiently separated events that cannot influence each other, they can even disagree about which occurred first. One observer may say that one distant event happened before another, while a differently moving observer gives the opposite order. Neither has made a mistake. There is simply no universal answer for those particular events. This sounds like a serious threat to causality, but relativity protects the causal relationships that matter. If one event can physically influence another, all observers agree about their causal order. A signal cannot be received before it is sent simply because someone changed their state of motion. So relativity did not destroy cause and effect, but it did remove something that had seemed closely connected to it. A single, universal sequence of everything happening throughout the cosmos. That lesson is already important. The order of events is not as absolute as ordinary experience suggests. Some events have a definite causal relationship. Others do not have a universal before and after at all. Nature distinguishes between events that can influence each other and events that are too separated for any signal travelling at an allowed speed to connect them. Causality survives, but it becomes tied to the structure of spacetime rather than to one cosmic clock. This was a major shift. Instead of imagining time as a universal river carrying every event forward together, physics began describing a spacetime in which different observers carve up events differently. The everyday rule that there must always be one answer to which thing happened first had already become more limited than it appeared. Then quantum mechanics made the situation even less comfortable. Quantum theory does not describe microscopic systems as though they simply possess all the familiar properties of ordinary objects while we happen to be ignorant of them. A quantum system can be described through several possible outcomes that coexist within the theory until an interaction produces definite result. This is not merely a matter of failing to know which possibility was secretly true all along. Experiments involving interference show that the possibilities can combine in ways that have observable consequences. The quantum world behaves as though alternatives can remain physically relevant together. A particle can be associated with more than one possible path. Different measurement outcomes can remain part of a shared quantum state. The theory does not always allow us to replace this with a simple hidden story in which everything possessed one definite classical history from the beginning. Once you become accustomed to that idea, a more unsettling question becomes possible. What if the uncertainty does not concern only where something is, or what result a measurement will produce? What if the order connecting events can also become quantum mechanical? Ordinarily, if two operations are performed on a system, we expect one of them to come first. Perhaps the first operation changes the system, and the second acts on the changed version. Reverse the order, and the result may be different. There is nothing mysterious about this. Washing a cup and then filling it with tea is preferable to filling it with tea and then deciding to wash it. The order matters because the first action creates the conditions encountered by the second. This is causal reasoning in its most ordinary form. Quantum theory allows researchers to investigate arrangements in which the order of operations cannot always be treated as one definite classical sequence. Under carefully controlled conditions, a quantum process can involve alternative orders together. Instead of simply saying that one operation definitely occurred first and another definitely occurred second, the full description can include both possible arrangements. This does not mean that someone in the laboratory sees an ordinary event happen backward. The equipment does not begin packing itself away before the experiment starts. The researchers still arrive before they leave. Their coffee still becomes colder rather than hotter. The unusual behavior appears in the quantum relationships connecting particular operations. Yet conceptually it matters enormously because it challenges an assumption so basic that we usually do not realize we are making it. We assume that underneath every process there must be one fixed answer to the question of what came first. Experiments involving what is commonly called the quantum switch have made this issue especially interesting. In such setups, the order in which two operations affect a quantum system can depend on another quantum degree of freedom. When that controlling system is prepared appropriately, the process cannot simply be understood as one ordinary order selected in advance. The two possible orders can participate coherently in the quantum process. Researchers can detect consequences of this structure, showing that the idea is more than a philosophical game. The interpretation of exactly what should be called indefinite causal order requires care, and physicists distinguish between different technical meanings of causal indefiniteness. But the basic lesson is enough for us at this stage. Quantum theory permits physical situations in which the familiar demand for a single fixed ordering of operations becomes difficult to maintain. This is where the phrase cause and effect begin to blur becomes useful, provided we do not make it more dramatic than the science allows. Nothing here tells us that effects routinely travel backward through time. Nothing gives us permission to change yesterday. Nothing suggests that logical contradictions are appearing in laboratories. The blur is more precise than that. It concerns whether causal structure itself must always be definite before a quantum process takes place. Classical thinking says that there should be a fixed network of possibilities telling us which events can influence which others. Quantum physics encourages us to ask whether that network may sometimes be part of the quantum description, rather than a rigid background behind it. The question becomes even harder when gravity enters the picture. In general relativity, gravity is connected to the geometry of space-time. Spacetime is not just an empty stage on which events happen. Its structure helps determine how objects move and which events can influence each other. Causal order is therefore linked to spacetime geometry. If two events are arranged so that a signal can travel from one to the other, there is a possible causal connection. If the geometry prevents such a connection, there is not. This works beautifully in general relativity, but general relativity is not a quantum theory. At very small scales or in extreme conditions, physicists expect that some deeper description combining gravity and quantum mechanics will be needed. Now imagine what follows if spacetime itself must become quantum mechanical. If the geometry that defines causal relationships is no longer perfectly definite, then perhaps causal relationships cannot remain perfectly definite either. This is one of the reasons the foundations of causality are connected to the search for quantum gravity. We do not yet have one experimentally confirmed final theory telling us exactly what happens. Different research programs approach the problem in different ways. Some treat spacetime as something that may emerge from more fundamental structures. Some investigate quantum networks of relationships from which familiar geometry could arise. Some study whether causal order itself should be treated as a basic ingredient, while others ask whether it can emerge along with spacetime. The details vary, but they share a remarkable possibility. The universe we experience may contain a stable causal structure, because a deeper level organizes itself into one, not because causal order was present in familiar form from the beginning. There is a useful comparison here with a crowd of people leaving a railway station. From a distance, you might see clear streams of movement. One group flows toward an exit, another moves toward the platforms. A broad pattern appears. You can describe the direction and speed of the crowd without following every individual footstep. At the smaller level, however, people are weaving, stopping, turning, avoiding luggage, checking phones, and occasionally realizing they're confidently walking toward the wrong platform. The smooth flow is real, but it is a large-scale pattern produced by many smaller interactions. Causality may turn out to have something of this character. At the level of ordinary objects, events settle into extremely reliable sequences. At a deeper level, the relationships may be less like a single line, and more like a collection of possibilities whose large-scale behavior produces the definite order we know. Entanglement adds another reason to be cautious about assuming that separate things with separate histories are always the best starting point. When quantum systems become entangled, the joint system can possess well-defined relationships even when the individual parts cannot be assigned independent properties in the classical way. Measurements on separated systems reveal correlations that cannot be reproduced by any simple model in which each particle merely carries a complete set of local instructions telling it how to respond. Entanglement does not allow useful messages to travel faster than light, so it does not overthrow relativistic causality. But it does change what we should regard as fundamental. Instead of beginning with independent objects and then adding relationships between them, quantum theory often makes the relationships impossible to ignore. This has encouraged a broader shift in some areas of theoretical physics. Perhaps relationships are more basic than the objects, locations, and sequences we normally use to describe them. If so, spacetime may emerge from patterns of quantum connection. Distances could reflect how strongly parts of a quantum state are related. Geometry could be a large-scale way of organizing those relations, and once a stable spacetime appears, ordinary causal order could appear with it. This is not established fact, and there is no single accepted theory that has completed the entire picture. But it provides a serious scientific framework in which the question makes sense, because before effect may be a property of the world we inhabit, without necessarily being one of the smallest pieces from which that world is built. Our own experience makes the opposite conclusion feel almost unavoidable, because we never encounter an indefinite breakfast, or a superposition of commuting routes in ordinary life. By the time physical systems become large enough for us to interact with directly, they're constantly exchanging information with their surroundings. Light scatters from them. Air molecules collide with them. heat moves through them. Their quantum relationships become entangled with enormous environments, and delicate quantum alternatives become extremely difficult to preserve. The world we see is therefore filled with stable records and definite outcomes. A chair stays where it is. A clock shows one reading. A broken glass remains broken. The microscopic strangeness does not disappear because quantum theory stops applying. Instead, interactions make the classical patterns overwhelmingly robust. Records are especially important when thinking about causality. Suppose a stone strikes a window and breaks it. Afterward, many traces exist. There may be fragments on the ground, vibrations in the wall, sound waves that travelled through the room, changes in the stone's motion, perhaps an annoyed neighbour who witnessed the event. The world has copied information about what happened into many places. Those records make the event effectively irreversible in practice. To undo it perfectly, you would need not only to rebuild the window, but also to reverse every physical consequence that carried information away from the collision. That includes effects scattered into the surroundings in ways you may never recover. Ordinary causes seem so definite partly because the macroscopic world continually creates records of them. This begins to connect causality with another familiar feature of reality, the arrow of time. We distinguish causes from effects partly because causes belong to what we call the past, and effects belong to what we call the future. But fundamental physical laws often do not contain the same obvious preference for one temporal direction that our experience does. Many microscopic processes can be described by laws that work consistently when the direction of time is reversed. The strong difference between past and future becomes most obvious in thermodynamics, where large systems tend to move from less probable organised conditions toward more probable disordered ones. A warm drink cools in a room because energy spreads into the surroundings. The reverse process is not forbidden by every microscopic law, but it is so fantastically unlikely for a large system that we never expect to see it. That means our sense of causal direction may be connected not only to quantum physics and spacetime but also to statistics. We live in a universe where records accumulate toward what we call the future. Entropy generally increases in that same direction, and memories contain information about one side of time rather than the other. A creature living inside such a world naturally experiences earlier events as causes and later events as effects. Whether that direction is fundamental or emerges from boundary conditions and large-scale behaviour is a deeper question, one we will return to later. For now, it is enough to notice how many assumptions are hiding inside something that once seemed simple. When you say that striking a match causes it to ignite, you're relying on a stable macroscopic world, a direction of time, physical laws governing chemical reactions, an environment that creates records, and a causal structure that allows one event to influence another. None of those ingredients is questionable in ordinary circumstances. Together they make causality feel inevitable. Yet when physicists examine each ingredient separately, the foundation becomes less obvious. Time is not universal. Quantum alternatives do not always possess definite classical histories. Entangled systems resist descriptions based entirely on independent local properties. Spacetime may itself require a quantum explanation. Some processes can even place different operational orders into a single coherent quantum description. Perhaps the surprising thing, then, is not that causality can become unclear at the deepest level. Perhaps the surprising thing is that it becomes so clear for us. We inhabit a world where causal order is stable enough that children learn it before they learn the word causality. Push the toy and it moves. Drop the cup and someone becomes unhappy. Press the button and something happens. Our brains build expectations from these patterns until they feel like necessary truths. Physics is asking whether necessity is really the right word. There may be a deeper structure in which what we call causes and effects are simply different parts of one network of relationships. There may be situations where causal direction becomes definite only after quantum possibilities interact with larger environments. There may be descriptions of spacetime in which the distinction between earlier and later is less fundamental than the correlations connecting events. There are even interpretations of quantum mechanics that explore whether later measurement settings can participate in the description of earlier quantum states without allowing ordinary messages to be sent into the past. None of these ideas has removed everyday causality, and none gives us a simple answer. They instead loosen the assumption that cause followed by effect must be the starting point of every possible physical description. That is the useful place to pause before going deeper. We should not abandon cause and effect, because almost everything around us demonstrates how well it works. We should simply stop assuming that its success settles the question of where it comes from. A property can dominate the world we see and still emerge from something very different underneath. The next step is therefore to look more carefully at the world that made causality seem fundamental in the first place. Long before quantum experiments forced anyone to wonder about indefinite order, ordinary physics had already given us powerful reasons to trust causal chains. Objects follow trajectories, signals arrive after they are sent, memories point backward, predictions work forward. The large-scale world does an exceptionally convincing job of presenting reality as a sequence in which one event produces the next, and understanding why that picture is so stable will make the deeper quantum exceptions much easier to recognize. That stability begins with something so ordinary that it is easy to overlook. Large objects are constantly interacting with their surroundings. A coffee cup is being struck by air molecules, warmed or cooled by the room, illuminated by light, pressed against a table, and pulled downward by gravity. A person walking through a hallway is exchanging heat with the air, reflecting light into nearby surfaces, making vibrations in the floor, disturbing dust, and leaving countless physical traces behind. Nothing in the everyday world is truly isolated. From the moment an object exists in an ordinary environment, information about it begins spreading into everything around it. That constant exchange is one of the main reasons the world appears definite, ordered, and strongly causal. At the quantum level, systems can behave in ways that have no simple classical equivalent. A particle can be described by several possible outcomes at once. Different alternatives can interfere with one another. The system does not always behave as though it secretly chose one ordinary path and simply refused to tell us which one. Yet delicate quantum possibilities are difficult to preserve when a system becomes entangled with a large environment. Every interaction carries information away. A photon scatters from the object, an air molecule collides with it, heat is exchanged, nearby matter responds. Very quickly, the different possibilities become correlated with huge numbers of environmental degrees of freedom. This process is known as decoherence, and it is one of the central reasons the large world does not look like an enlarged version of a quantum experiment. Decoherence does not mean that quantum mechanics suddenly stops working once an object becomes large. Quite the opposite. The process is itself quantum mechanical. What changes is our ability to observe the delicate interference between alternatives. Imagine trying to keep two versions of a physical situation perfectly isolated so that they can later interfere with each other. That is difficult enough with a carefully controlled microscopic system. Now imagine trying to do it with a warm object sitting in a room full of air and light. Every collision with the environment effectively carries away information about the system. The surrounding world becomes involved. Keeping the alternatives coherent would require controlling an enormous number of interactions with ridiculous precision. A laboratory can sometimes protect carefully prepared quantum systems for useful periods of time, but a mug on your desk is not receiving that level of special treatment. It is being enthusiastically monitored by the universe, whether you ask for that service or not. This helps explain why objects around us appear to occupy definite states. You do not look at your chair and find it visibly spread across two corners of the room. You do not put your keys on the table and later discover that they maintained a delicate quantum alternative between being on the table and being inside the refrigerator, although ordinary forgetfulness can sometimes create an equally confusing investigation. The reason is not simply that chairs and keys are too large to obey quantum physics. Their size makes them interact with enormous numbers of surrounding particles, and those interactions rapidly destroy the observable interference between different macroscopic possibilities. What remains is a world that can be described extremely well in terms of stable, effectively classical outcomes. Once outcomes become stable, causal stories become easier to construct. Suppose a ball rolls across a table and knocks over a glass. Before the collision, the ball has a particular macroscopic trajectory. After the collision, the glass changes motion, falls, and perhaps breaks. Light bouncing from the scene carries information outward. Sound waves travel through the air. Vibrations move through the table and floor. Fragments scatter. Anyone nearby may see or hear what happened. A camera may record it. The event creates many physical records, and those records agree with one another. They all support the same ordinary sequence. The ball approached, the collision occurred, the glass fell, and the fragments appeared afterward. This redundancy is important. Everyday events do not normally leave just one fragile piece of evidence. They create many copies of information in the environment. You can learn that a tree is standing outside without touching it, because light reflected from the tree reaches your eyes. Someone else can see the same tree from another angle. A camera can photograph it. Its shadow falls on the ground. Wind moves its branches. The environment contains many records of the tree's position and condition. Large-scale reality therefore becomes publicly accessible in a way that microscopic quantum states often are not. Different observers can examine different pieces of the environment and still agree about what happened. That agreement makes causal structure feel objective. If you hear a crash from the next room and then walk in to find a plate shattered on the floor, several clues point toward an earlier event. The pieces are spread outward from where the plate struck. Perhaps a chair was knocked slightly aside. Maybe someone saw the plate fall. The sound reached you only after the impact occurred. All of these physical records fit one sequence much better than the reverse sequence. You do not seriously consider the possibility that the fragments caused themselves to assemble into an earlier falling plate, while the sound travelled backward toward the collision. The microscopic laws governing the materials may allow many motions in principle, but the macroscopic arrangement of records overwhelmingly favours one direction. Thermodynamics strengthens this effect. Large systems can be arranged in relatively special states or in vastly more numerous ordinary states. A neatly stacked deck of cards is one recognisable arrangement. A scattered pile can take an enormous number of different forms. A drop of ink placed in water begins concentrated in one region, then spreads. Once it has dispersed, there are vastly more microscopic arrangements corresponding to the mixed state than to the original concentrated state. This statistical tendency is described through entropy. In ordinary isolated macroscopic processes, entropy tends to increase. Energy spreads out. Ordered arrangements become less special. The number of microscopic possibilities compatible with what we observe generally grows. That gives the everyday world a strong direction. A warm cup of tea left in a cooler room loses heat to the surroundings. The reverse process, in which random molecular motion in the room somehow coordinates itself so that energy flows into the cup and makes the tea hotter without another energy source, is not forbidden in the simple sense that every individual molecular collision would violate physics. The problem is probability. There are overwhelmingly more microscopic arrangements corresponding to heat spread through the environment than arrangements in which all the relevant motions cooperate to concentrate that energy back into the drink. For a large object containing an enormous number of particles, the reverse behaviour becomes so improbable that we treat it as impossible for practical purposes. The same logic applies to many events we instinctively associate with causation. A glass can fall and shatter because there are countless ways for its ordered structure to become a disordered collection of fragments, vibrations, heat, and sound. The reverse sequence would require an extraordinary coordination of particles. Shards would have to leap from different locations, meet with exactly the right positions and velocities, reconnect their molecular structures, recover heat dispersed into the surroundings, reverse vibrations in the floor, draw sound waves back from the room, and reconstruct the precise state that existed before the impact. Nothing about ordinary experience prepares us to expect that, because the number of possible disordered states is vastly larger than the number of states corresponding to one intact glass sitting quietly on a table. This thermodynamic direction is closely connected to our idea of cause and effect. Causes usually appear on the side of the event where information is concentrated in a smaller number of conditions. Effects spread that information into many places. Strike a bell and one localized action produces vibrations in the metal, sound waves in the air, movements in nearby objects, electrical signals in microphones, and neural activity in anyone who hears it. The original event becomes recorded across the environment. Reconstructing the exact original strike from every later consequence would be extremely difficult. Going forward, however, is easy. The bell is struck and the effects spread. Our memories participate in this same direction. Remembering something is a physical process. A memory requires changes in the brain. Neural activity modifies connections and creates records of earlier events. Those records consume energy and contribute to the same thermodynamic processes occurring everywhere else. We remember the past because earlier events have left physical traces that exist now. We do not remember the future because future events have not yet produced those traces in our present physical state. This sounds obvious when stated in everyday language, but it becomes significant when we ask why psychological time and physical time point the same way. Our brains are not standing outside the universe observing its direction. They are physical systems operating within the same thermodynamic conditions. Because memory points toward earlier events, our entire experience is organized causally. You remember placing the kettle on the stove and then hearing it boil. You remember opening the door and then stepping outside. You do not experience both moments from some neutral perspective. One is stored as a condition that preceded the other. Learning strengthens the pattern. A child discovers that pressing a button makes a toy produce a sound. After enough repetitions, the child expects the effect. The brain begins predicting what will happen after particular actions. Much of perception itself involves prediction. The nervous system is continually using earlier information to estimate what comes next. This predictive structure is enormously useful for survival. An animal that can connect a sound with an approaching predator has an advantage over one that treats every event as unrelated. A person who learns that touching fire causes injury tends not to require endless experimental confirmation. Human beings take this further by building detailed models of causal relationships. We ask what produced a storm, what caused a machine to fail, what led to an illness, what made an economy change, or why someone behaved in a particular way. Sometimes our causal explanations are correct. Sometimes we confidently invent connections that are not there. The brain is so eager to find causes that it can detect patterns in coincidence, which is why superstition and questionable explanations are never in short supply. Still, the tendency exists because reliable causal structure is genuinely useful in the macroscopic world. The stability of large-scale objects also allows causes to be separated from background noise. Imagine trying to understand causation in a world where every object constantly changed into visibly different states with no persistent identity. It would be difficult to say what acted on what because nothing would remain recognizable long enough to track. Everyday objects are different. A baseball remains identifiable as it travels through the air. A car remains the same car as it moves down a road. A planet maintains enough stability that astronomers can track its position across years. Because macroscopic objects persist, we can describe interactions between them in a straightforward way. One object approaches another. They interact. Their later states depend on the encounter. Classical physics takes advantage of this stability. At ordinary scales and ordinary speeds, the complicated quantum behavior underneath averages into patterns that can be described with remarkable accuracy. Engineers do not need to calculate the quantum state of every atom in a bridge to determine whether the bridge can support traffic. Astronomers predicting a planet's orbit do not have to follow every quantum fluctuation in every particle making up the planet. The large-scale variables are stable enough that simpler descriptions work. Position, velocity, temperature, pressure, force, and other macroscopic quantities behave predictably within the relevant conditions. That predictability reinforces our causal intuition. When the same preparation repeatedly produces the same general result, we naturally treat the preparation as a cause. Release an unsupported object near Earth's surface and it accelerates downward. Heat water sufficiently and it boils. Apply the brakes on a moving bicycle, and friction reduces its motion. These relationships can be measured, tested, and used to make reliable predictions. They remain dependable even if the microscopic description underneath contains probabilities. Large numbers of particles often smooth quantum uncertainty into extremely consistent collective behavior. A useful example is radioactive decay. For an individual unstable nucleus, quantum theory does not generally tell us the exact moment when it will decay. It gives probabilities. Yet take a large sample containing enormous numbers of such nuclei, and the overall decay becomes statistically predictable. We can describe how the population changes over time with extraordinary reliability, even though individual events remain unpredictable. The large-scale pattern is stable, because fluctuations average out. Something similar occurs throughout statistical physics. Microscopic uncertainty does not imply macroscopic chaos. Huge collections of particles can produce regular behavior precisely because individual variations become insignificant compared with the whole. This is one reason emergent causality is not as strange as it first sounds. A deeper level can contain probabilities and indefinite alternatives, while a higher level displays dependable sequences. We already accept this kind of transition elsewhere. Gas pressure is stable even though individual molecules move unpredictably. Temperature changes smoothly, even though microscopic particles collide in complicated ways. The position of a large object can be well defined for practical purposes, even though its constituents obey quantum mechanics. There is no requirement that the properties useful at one scale must appear unchanged at every smaller scale. The environment also selects which kinds of macroscopic information remain stable. Certain states survive interaction better than others. A definite approximate position, for example, can become repeatedly recorded in surrounding particles. Light bouncing from an object carries information about where the object is. This makes position especially natural in the classical world. Other delicate quantum relationships are rapidly dispersed into the environment and become inaccessible. The world we experience is therefore not a random selection of all quantum possibilities. It is dominated by robust states that can leave many consistent records. Once those records exist, history becomes difficult to erase. Consider footprints across wet ground. The person who made them may have left, but the surface retains information about where pressure was applied. Rain may eventually remove the marks, but until then they function as evidence of an earlier interaction. A photograph works similarly. Light from an earlier scene changes a physical recording medium. A fossil preserves traces of an organism. Tree rings preserve information about earlier growth conditions. Ice cores preserve information about ancient atmospheres. The world is filled with material systems that store information about earlier states. These records create an asymmetry between what we call past and future. We can examine evidence of yesterday, because yesterday interacted with the present. There are no comparable ordinary records of tomorrow sitting around waiting to be discovered. This is one reason causes seem naturally associated with the past. We infer them from traces. The effect is available to us now, while the cause has often already happened. By reconstructing the cause from its records, we build a history. Science does this constantly. Geologists reconstruct ancient environments from rocks. Astronomers infer stellar histories from light and chemical composition. Detectives reconstruct events from physical evidence. Doctors infer physiological processes from symptoms and measurements. Much of knowledge consists of reading present records to infer earlier conditions. Prediction operates in the other direction. From current conditions and known regularities, we estimate what will happen later. The two activities feel different. The past seems fixed and documented. The future seems open and uncertain. Yet part of this difference may come from our information. We possess records of the past, but not the future. Even in a deterministic classical model, where future states follow from present conditions, limited knowledge prevents us from calculating everything. Weather is a familiar example. The atmosphere obeys physical laws, but tiny uncertainties in initial conditions can grow, making long-range prediction difficult. Causality remains intact even when prediction fails. Not knowing the effect is not the same as there being no cause. This distinction becomes important when we later return to quantum mechanics. Uncertainty by itself does not destroy causality. Randomness by itself does not prove that causal order is absent. A process can contain unpredictable outcomes while still having a definite sequence of operations. If a quantum measurement produces one of several possible results, we can still say that the preparation occurred before the measurement and that the measurement occurred before the recorded outcome. To challenge causal order itself requires something more subtle than ordinary uncertainty. That is why experiments involving indefinite causal order attract so much interest. They are not merely demonstrations that quantum results can be unpredictable. They investigate whether the arrangement of operations can resist being placed into one fixed order in the first place. The everyday world hides that possibility extremely well, because almost everything around us is continuously decohering, producing records, increasing entropy, and interacting with environments that reinforce definite histories. By the time information reaches our senses, the underlying quantum alternatives have usually become inaccessible as coherent alternatives. We receive one stable sequence. The cup fell. The door opened. The light turned on. We can imagine other possibilities, but we do not observe them interfering with the history we actually record. Language then strengthens the habit. Most ordinary sentences place actions into causal structures. Someone opened the window so the room became colder. The alarm rang so you woke up. The road was icy, therefore the car lost traction. Even when causality is not stated explicitly, grammar tends to arrange events into subjects, actions, and consequences. We tell stories in sequences because sequence is how memory works and how communication remains understandable. Try describing an ordinary morning without using temporal or causal relationships, and the result quickly becomes difficult to follow. Breakfast, waking, getting dressed, leaving home, and arriving somewhere makes sense largely because they occupy an order. Society is also built around causal responsibility. We ask who caused damage, which decision produced a result, what action led to an outcome, and what could have prevented it. Law depends on distinguishing correlation from causation. Medicine depends on identifying treatments that produce beneficial effects rather than merely occurring alongside recovery. Engineering depends on finding failure mechanisms. Everyday planning depends on expecting actions to influence later situations. Causality is so deeply embedded in practical life that a world without it would not merely feel strange. Most familiar forms of reasoning would stop functioning. None of this proves that causality must be fundamental. It shows why the opposite idea is so difficult to accept. Our scale is almost perfectly designed to make causal structure visible. We are large compared with atoms, slow compared with light, warm compared with many delicate quantum systems, and surrounded by environments that rapidly destroy accessible coherence. We live in a thermodynamic regime where records accumulate in one direction. Our brains evolved to recognize regularities in that same environment. Our memories preserve earlier events. Our language organizes sequences. Our technologies exploit predictable responses. Everything points toward one simple conclusion, that causes happen first and effects follow. Yet this conclusion may describe the stable surface rather than the deepest rule. The fact that a property is unavoidable at our scale does not tell us whether nature begins with it. Temperature is unavoidable when discussing ordinary matter, but temperature is not assigned to an isolated fundamental particle in the same way it is assigned to a room. Fluid flow is unavoidable when discussing rivers, but a single molecule is not a river. Biological function is essential when discussing a heart, but no isolated carbon atom has a heartbeat. The larger structure introduces concepts that become meaningful only when enough components interact in particular ways. Causal order may emerge through a similar process. Once quantum systems interact with environments, once stable records form, once thermodynamic asymmetry becomes overwhelming, and once space-time provides a reliable structure connecting events, the world can behave as though definite causal order were built into everything. At that level, saying that one event caused another is not an approximation in any useless sense. It is the correct language for the scale. The possibility under investigation is simply that the deeper description may not use that language in the same way. This is why the everyday world can remain perfectly causal even if the foundations are less definite. Nothing about your morning routine requires the deepest structure of reality to resemble your morning routine. The causal order you experience may be the result of many conditions working together, including decoherence, stable macroscopic states, thermodynamic irreversibility, environmental records, and the geometry of space-time. Remove those conditions one by one, especially in carefully controlled quantum experiments, and assumptions that looked universal begin to loosen. The next difficulty appears when physicists stop asking whether an event has an uncertain outcome and start asking whether two operations have a definite order at all. That is a much sharper question. It moves beyond familiar quantum randomness and toward processes in which the usual statement that one thing happened before another may not provide a complete description. To see why that possibility is so unusual, we have to leave the noisy macroscopic world where the environment continually forces events into stable histories, and look at quantum systems carefully isolated enough that different alternatives can remain coherent long enough to reveal what ordinary experience has been hiding. The hidden strangeness becomes easier to see once we stop asking what a quantum system will do and start asking a more basic question about the events themselves. In ordinary life, an event appears to come with a position in a sequence. A door is closed, someone turns the handle, the door opens, and then someone walks through it. We may not know every microscopic detail of what happened, but there is no serious uncertainty about the order. Turning the handle occurs before the door opens. Opening the door occurs before walking through the doorway. Rearranging those events changes the story and in some cases makes the story impossible. This is so normal that we usually treat order as part of the background rather than something physics needs to explain. Quantum mechanics makes that assumption less comfortable, because it allows alternatives that would normally be mutually exclusive to remain together in a single physical description. Once that becomes possible, the idea that every process must possess one definite sequence from the beginning becomes something we have to examine rather than simply assume. The familiar way to approach quantum mechanics is through uncertainty about properties. A particle may not have one definite position that is merely hidden from us. A measurement can produce one of several possible outcomes, and before that measurement the theory represents those possibilities together. This is already different from ordinary ignorance. If you place a coin under a cup without looking, the coin is still either heads or tails. You simply do not know which. Quantum alternatives can behave differently, because they can interfere. The possibility is not merely separate answers sitting in a box while we wait to discover the correct one. Their relationship can affect what is later observed. This is why quantum experiments involving paths, spins, polarization, and other physical properties can produce patterns that have no simple classical explanation, based on a system secretly choosing one ordinary alternative in advance. A useful way to think about this is to imagine a traveller approaching two possible routes through a landscape. In ordinary reasoning, the traveller chooses the left path or the right path, even if you're too far away to see which choice was made. Your uncertainty concerns knowledge. There is still a fact about the route. In a quantum experiment, the situation can be arranged so that the alternatives remain coherent. The system behaves in a way that depends on both paths being part of the physical description. Later, those alternatives can meet again and interfere. The outcome can depend on their relative relationship in a way that would make no sense if the system had simply selected one path and ignored the other. The analogy is imperfect because quantum systems are not tiny indecisive hikers wandering through miniature forests, but it captures the important point. Quantum possibilities can remain physically connected until interactions with the environment or a measurement make the alternatives effectively distinguishable. Once we accept that different possibilities can coexist coherently, another possibility becomes difficult to avoid. Why should the uncertain property have to be position, direction, or some other familiar quantity? Could the uncertainty concern the ordering of operations themselves? Imagine that a quantum system must undergo two different physical processes. In an ordinary experiment, we would arrange the equipment so that the system encounters the first operation and then the second. We could also reverse the setup so that the second occurs first and the first occurs afterward. These two arrangements may produce different results, because the effect of an operation can depend on the state created by whatever happened before it. That is perfectly normal. Washing a surface and then painting it is not generally equivalent to painting it and then washing it. Order can matter. Classically, however, one of those orders must be the actual order. Even if we toss a coin to decide which arrangement to use, the process remains definite once the choice is made. Perhaps the coin lands one way, and the first operation occurs before the second. Perhaps it lands the other way, and the second occurs before the first. We may describe the overall experiment using probabilities, because we did not know which arrangement would be selected, but every individual run still belongs to one ordinary sequence. There is always an answer to the question of what happened first. This is sometimes called a classical mixture of orders. We are uncertain about which order occurred, but the physical process itself is not indefinite. Quantum mechanics allows a more unusual possibility. Instead of using an ordinary random choice to select the order, the choice can be controlled by a quantum system that remains in a coherent combination of alternatives. In that case, the total experiment may contain one ordering and the reverse ordering together in a way that can later produce interference. The distinction between these situations is crucial. Simply being ignorant about order is not the same thing as having an indefinite quantum order. A shuffled playlist contains uncertainty about which song comes next until you look, but the device still plays one song before another. A quantum process can be arranged so that treating the order as secretly fixed can fail to capture the full physical description. This is where ordinary language starts becoming awkward, because our verbs are built for definite sequences. We want to say that one operation happened and then another happened. We want to place every event along a single line. Quantum theory can force us to describe something less familiar. The alternatives are not necessarily separate histories with one secretly chosen as the real history. They can remain coherent parts of a common process. Asking which one happened first may then resemble asking which path a particle definitely took in an interference experiment, when the experimental result depends on the paths not being treated as independent classical alternatives. The question feels natural, but the physical setup may not provide the kind of answer the question assumes. It is important not to turn this into the claim that time itself disappears whenever a quantum system enters a laboratory. Standard quantum mechanics still uses time to describe how states change. Researchers switch equipment on, prepare systems, perform operations, and record results in an ordinary sequence. Their clocks do not become confused. The laboratory remains embedded in a perfectly familiar macroscopic world. What becomes indefinite is a more specific relationship inside the quantum process. The system can be arranged so that the order of particular operations is not represented by one fixed classical sequence. This distinction prevents a great deal of unnecessary mystery. We are not saying that the entire history of the room loses its order. We are saying that quantum mechanics can place the ordering of selected physical operations into the same kind of coherent structure that it places other physical alternatives. That difference also explains why you cannot simply look at the setup and expect to see a dramatic violation of normal time. If you tried to determine the order too directly, you would generally create information distinguishing the alternatives. Once the two possibilities become distinguishable in the environment, the coherence connecting them is reduced or lost. This is the same reason ordinary quantum interference requires careful control. The strange behavior appears only when the alternatives remain sufficiently indistinguishable that the physical process retains information about their relationship. Quantum experiments are often less like watching a bizarre event happen in front of you, and more like arranging conditions so carefully that the final statistics reveal something ordinary classical histories cannot reproduce. Indistinguishability is therefore doing a great deal of work. Suppose two routes through an experiment lead to exactly the same final situation, and nothing in the environment records which route was taken. Quantum theory allows the alternatives to combine. Change the experiment so that some detector, stray photon, surrounding molecule or other interaction leaves reliable information about the route, and the interference can disappear. The important feature is not human awareness. Nobody needs to sit beside the experiment staring thoughtfully at it. What matters is whether the alternatives have become physically distinguishable through correlations with other systems. Measurement in this sense is not about consciousness. It is about information becoming embedded in physical degrees of freedom. The same principle becomes relevant when the alternatives concern order. If the environment records that the first operation definitely happened before the second, and that information becomes available in a stable macroscopic form, then we have an ordinary causal sequence. If the experiment instead preserves coherence between the two orders, the final behavior can retain contributions from both possibilities. The order then functions less like a hidden item waiting to be discovered, and more like a genuine quantum feature of the process. This does not mean that the words before and after become meaningless everywhere. It means that they may not always apply to the internal structure of the process in the simple classical way we expect. There is a temptation here to imagine two entire universes, one in which the first operation happened first, and another in which the second operation happened first, somehow layered over each other. That picture can be useful as a rough intuition, but it can also mislead. Quantum mechanics does not require us to picture fully formed classical worlds sitting side by side. What the theory provides is a mathematical description of possible alternatives and the way their amplitudes combine. Since we are avoiding equations, the safest verbal version is simply that the alternatives remain part of one quantum process and can affect the observed outcome together. Trying to force them too early into ordinary stories can make the situation seem either more mystical or more familiar than it really is. The deeper point concerns what we mean by an event. In classical physics, we tend to imagine events as facts occurring at particular places and times. Once an event has happened, it can be placed in relation to other events. One was earlier, one was later, one may have influenced another. Quantum mechanics complicates this picture because some properties associated with a process may not possess definite classical values before the relevant interactions take place. If causal order itself can become one of those properties, then the structure connecting events is no longer guaranteed to exist as a fixed background independent of the quantum system. This is an important step because traditional physics usually assumes the stage before describing the actors. In Newtonian physics, time provides a universal sequence. Events happen within it. In relativity, the situation is more sophisticated, but spacetime still provides a causal structure that determines which events can influence which others. Quantum fields then evolve within that spacetime. The causal relationships are normally taken as given. A signal can travel from one region to another only when spacetime permits it. The background tells us which influences are possible before we begin calculating the details of the quantum process. The possibility of indefinite order suggests a different approach. Perhaps, at least in some quantum situations, the ordering structure should not always be supplied in advance. Perhaps it can become part of the physical state we're describing. That idea sounds radical, only because causality has usually occupied such a privileged place. We're comfortable allowing a particle to have an indefinite position. We're comfortable allowing a photon to involve more than one possible path. We're less comfortable allowing the order of operations to become indefinite, because order feels closer to the architecture of reality itself. Changing the position of an object changes something inside the universe. Changing causal order seems to change the way the universe is arranged. This is also why physicists use careful terminology when discussing these experiments. Not every quantum superposition involving different paths is automatically an example of indefinite causal order. Not every situation in which observers are uncertain about timing qualifies. Not every delayed measurement means the future influenced the past. The scientific question is more precise. We want to know whether a process can be represented as a fixed causal ordering of operations, perhaps with ordinary uncertainty about which ordering occurred, or whether the process contains genuinely quantum relationships between different possible orders. That distinction matters because the first situation can still be understood within a classical causal framework. The second may require a broader framework in which causal structure itself is not always definite. Ordinary probability provides a helpful comparison. Imagine two people entering a building through separate doors. You do not know who entered first because you were not watching. There is uncertainty, but there was still an actual order. Perhaps one arrived several seconds before the other. Your ignorance does nothing to change that. Now imagine a physical experiment where treating the alternatives as merely unknown classical sequences fails to reproduce the observed behavior, because interference between the sequences matters. The uncertainty is no longer just in your head. The structure of the experiment reflects the combination of alternatives. That is much closer to the quantum situation physicists are interested in. The reason interference matters so much is that it gives us a way to distinguish genuine quantum coherence from ordinary lack of information. If two alternatives are merely random possibilities, probabilities are added in the familiar way. One happened or the other happened, and we combine our uncertainty about them. When quantum alternatives remain coherent, their contributions can reinforce or cancel each other before probabilities are assigned to final outcomes. This is the same underlying feature that produces familiar interference phenomena in quantum physics. Applied to order, it means that one sequence and the reverse sequence can contribute jointly to what is observed rather than behaving like separate entries in a classical lottery. None of this gives a usable method for violating the normal constraints of communication. Quantum theory remains remarkably careful about that. Entanglement produces correlations that defy classical explanation, but it does not let us send controllable information faster than light. Indefinite order can provide advantages for certain information processing tasks, but it does not mean someone can place a message in a machine and receive the reply before asking the question. The unusual causal structure exists within strict operational rules. Physics becomes stranger without becoming arbitrary. This is worth emphasizing because popular descriptions of quantum mechanics often leap too quickly from uncertainty to statements that anything can happen. That is almost the opposite of the truth. Quantum mechanics is extraordinarily restrictive. It permits behavior that classical intuition does not expect, but it predicts that behavior with remarkable precision. A quantum experiment does not produce whatever result happens to feel mysterious enough. The possible outcomes and their relationships are tightly constrained by the theory. Indefinite order, where it appears, is therefore not a breakdown of law. It is a different lawful structure. The distinction becomes clearer if we think about causality as a set of permissions. In an ordinary causal network, one event may influence another because it lies earlier in the appropriate structure. Another pair of events may be unrelated because neither can send information to the other. Once the network is fixed, we can reason about which correlations might result from common causes and which could come from direct influence. Much of science uses causal reasoning in exactly this way. We observe patterns and ask what arrangement of influences could have produced them. Quantum mechanics complicates these networks because correlations can arise through entanglement without behaving like ordinary shared hidden information. Indefinite order takes another step by asking whether the network itself must always have a fixed direction. Instead of saying that the first operation can influence the second but not the reverse, we can investigate a process where neither single directional description captures the entire quantum arrangement. The network is no longer merely carrying quantum systems. Something about the ordering structure is quantum as well. This can sound as though we have abandoned the meaning of cause entirely, but that would be premature. Even in these experiments, researchers still talk about inputs, operations, outputs, communication, and correlations. The concept of influence remains useful. What changes is the assumption that all influence must fit inside one globally fixed sequence. A more general theory can contain ordinary causal order as one possibility while also allowing structures that cannot be reduced to it. In that sense, indefinite order does not erase causality. It enlarges the space of causal possibilities. There is another subtle point hiding underneath all of this. The words before and after normally refer to time, while causal order refers to influence. The two are closely related but not identical. In relativity, distant events can have different temporal orderings for different observers if they cannot causally affect each other. Their before and after relationship is not absolute, yet causality remains safe because no physical signal connects them. When physicists discuss indefinite causal order in quantum processes, they're often focusing on operational influence rather than claiming that laboratory clocks literally disagree about which macroscopic event occurred earlier. Keeping temporal order and causal order separate prevents us from imagining paradoxes that the experiment does not actually create. This is one reason the subject becomes difficult to describe in ordinary language. Everyday conversation bundles time, order, influence, and explanation together. We say the spark happened first and therefore caused the fire. We say the impact occurred before the sound reached us and therefore produced the sound. In familiar situations, these concepts line up so well that distinguishing them seems unnecessary. Quantum physics forces the distinctions apart. An ordering of laboratory procedures, an ordering of operations experienced by a quantum system, and a causal relationship describing which operation can influence another may not always be identical concepts. That separation becomes especially important when space-time itself enters the discussion. In the experiments we have been considering, the laboratory still sits inside ordinary space-time. The researchers are not creating regions where general relativity stops working. Instead, they use quantum control to create a process whose operational order cannot be represented in the usual fixed way. This already shows that causal structure can become less classical than everyday experience suggests. But quantum gravity raises a more profound possibility. If space-time itself eventually has to be described quantum mechanically, then the geometry that usually determines causal order could become indefinite too. Imagine two events whose order depends on the gravitational field between them. In general relativity, matter and energy influence space-time geometry, and space-time geometry determines the causal relationships between events. If the matter creating the gravitational field could occupy a genuinely quantum combination of configurations, then the associated geometries might also have to be treated quantum mechanically. In one configuration, a certain event might lie earlier in the relevant causal structure. In another configuration, the ordering might differ. A complete theory of quantum gravity would have to tell us what such a situation actually means. We do not yet possess that complete experimentally verified theory, but the question shows why indefinite causal order is not merely a clever laboratory curiosity. It may be pointing toward the kind of conceptual language needed when quantum mechanics and spacetime finally meet. For now, however, the laboratory version is already enough to unsettle the old picture. The universe does not seem obliged to assign every selected quantum operation one definite place in a classical sequence before anything happens. Under the right conditions, alternatives involving different orders can remain coherent. The final observations can depend on that coherence. If we insist that one order must secretly have been real all along, we risk importing a classical story that the experiment does not require. Notice how far this is from everyday experience. When you prepare breakfast, there is no useful sense in which pouring the cereal before adding the bowl coherently combines with adding the bowl before pouring the cereal. The environment records everything too strongly. The bowl has a definite macroscopic location. Your hands interact with trillions of particles. Light, heat, sound, and air continually distinguish what happened. Any delicate quantum relation between alternative orders disappears so quickly that classical sequence becomes overwhelmingly adequate. This is why indefinite order had to be discovered through carefully engineered quantum systems rather than through suspicious behavior at the kitchen table. The fact that the phenomenon requires such careful isolation tells us something important. Definite order may not need to be fundamental in order to dominate ordinary reality. It may emerge because large systems cannot preserve the coherence required for alternatives in causal order to remain observable. The classical world then settles into histories where operations can be arranged consistently. Records agree about what happened, and causes appear securely before effects. At our scale, that is the only structure we normally encounter. The question now becomes whether this quantum indefiniteness is merely a peculiar way of arranging operations, or whether it tells us something deeper about causality itself. To answer that, we need to examine the most famous example more carefully. Instead of talking generally about two possible orders, we can look at how physicists construct a process in which the order is controlled by a quantum system, how the alternatives remain coherent, why the result cannot simply be treated as ordinary randomness, and what it actually means to say that neither operation has one unquestionable claim to having happened first. That takes us directly into the quantum switch, where causal order stops being a fixed instruction and becomes part of the quantum experiment itself. The quantum switch gives us a particularly useful way to see how strange this idea really is, because it takes something completely ordinary, the order in which two operations are performed, and turns that order into something that can behave quantum mechanically. Imagine that a small quantum system is sent through two devices. Each device changes the system in some controlled way. In a normal experiment, the arrangement is straightforward. The system reaches one device first and the other device second. Reverse the equipment and you reverse the order. Nothing about this is mysterious. The first operation changes the system that reaches the second operation, so changing the order can change the final result. The important point is that in either arrangement there is always a definite answer to the question of which operation came first. Even if someone chooses the order randomly, every individual run still has one actual sequence. The randomness may prevent you from knowing the order in advance, but nature is not uncertain about it in the same sense. One operation happened first and the other happened afterward. The quantum switch changes this by making the order depend on another quantum system rather than on an ordinary classical choice. Instead of a person deciding which device comes first, a quantum degree of freedom controls the route through the experiment. In one alternative, the target system experiences the first operation and then the second. In the other alternative, it experiences the second operation and then the first. When the controlling system is prepared so that these alternatives remain coherent, the total process can contain both orders together. The important word here is coherent. If we simply chose between the two orders by flipping a coin, we would have ordinary uncertainty. Perhaps one sequence occurred, perhaps the other occurred, and we would assign probabilities because we did not know which one was selected. In the quantum switch, the alternatives can remain connected in a way that allows them to interfere. They are not merely two possible classical stories placed into a bag and selected one at a time. That distinction can sound technical, but there is a simple reason it matters. Imagine that someone places two envelopes on a table while you're outside the room. You return and do not know which envelope was placed down first. Your ignorance does not mean their order was indefinite. There was an actual sequence. A security camera could settle the question. Someone who watched the event could tell you. The information exists even though you do not possess it. Quantum indefiniteness is different. In the relevant experimental description, treating the process as though one definite order secretly occurred and we simply failed to observe it can lose the feature responsible for the final interference. The two alternatives must remain physically connected as parts of a single quantum process. This is why the phrase "neither event comes first" needs to be handled carefully. It does not mean that two macroscopic events occur at exactly the same moment. It does not mean that laboratory clocks stop working. It does not mean that researchers can watch an effect appear and then casually wait for its cause to arrive a few seconds later. What becomes indefinite is the causal order of particular quantum operations within a controlled process. The laboratory itself still has ordinary equipment, ordinary preparation procedures, and ordinary measurements. Someone switches the apparatus on before collecting the results. The experiment does not erase normal time from the room. The unusual feature is that the target system can encounter two operations in a quantum arrangement for which no single classical ordering captures the whole process. One common way of realizing this idea uses different paths available to a photon. Along one path, the photon can encounter two optical operations in one sequence. Along another path, it encounters the same operations in the opposite sequence. If the photon is prepared so that the path information remains quantum mechanically coherent, the two orders are associated with alternatives that can later be recombined. The final measurement can then reveal interference linked to the relationship between the two orders. What matters is not that the photon somehow feels confused about which device is closer. The experiment has been arranged so that the order is tied to a quantum property that has not been reduced to one classical alternative. This immediately raises a reasonable objection. Perhaps the photon simply travels along one path or the other, and we happen not to know which one. That would restore the familiar picture. One path would correspond to one order, and the other path would correspond to the reverse order. Every photon would still experience a perfectly definite sequence, while the experimenters merely lacked information about which sequence occurred. The reason quantum physicists do not stop there is the same reason they do not explain ordinary interference experiments by saying that a particle secretly chose one path and nothing else mattered. When coherent alternatives are recombined, the observed behavior depends on the relationship between those alternatives. Destroy the coherence by allowing reliable information about the path to escape into the environment, and the interference changes or disappears. Preserve the coherence, and the alternatives continue to affect the final result together. This is not a philosophical preference about how mysterious we would like the world to be. It is an operational difference between an ordinary mixture and a quantum superposition. In an ordinary mixture, each run follows one alternative, and probabilities describe our uncertainty about which one. In a coherent quantum process, the alternatives can combine before the final probabilities appear. That combination can produce behavior unavailable to the corresponding ordinary random mixture. The quantum switch is interesting because the thing being coherently controlled is not merely a location or a polarization. It is the ordering of transformations acting on the target system. Suppose the first operation changes some property of the target and the second operation then acts on that changed property. Reversing the order gives a different transformation because the second operation now acts first. If the control is ordinary, we obtain one sequence or the other. If the control is quantum and coherence is preserved, information about both sequences can contribute to the final state. By later measuring the control appropriately, researchers can reveal interference between these possibilities. The process behaves differently from simply forgetting which fixed order was used. That is the central reason physicists describe the order as indefinite. The word causal enters because order determines possible influence. In a definite sequence, the earlier operation can affect what reaches the later operation. If the first device acts before the second, then the second device receives a system that may already contain changes introduced by the first. In that arrangement, information can effectively flow through the sequence in one direction. Reverse the order and the direction of that operational influence reverses as well. A fixed causal structure tells us which operation has the opportunity to affect which other operation through the system passing between them. When both possible orders participate coherently, the usual causal description is no longer reducible to one of those directions. Physicists have developed ways to describe processes without assuming from the beginning that every operation must occupy one predetermined causal order. This is useful because the traditional quantum circuit model normally has a built-in sequence. A quantum gate acts, then another gate acts, then perhaps another. The states may be highly quantum, entangled and uncertain, but the circuit diagram itself usually provides a definite ordering. The wires tell you what can feed into what. The quantum switch asks whether the order of the gates can itself become part of the quantum information being manipulated. That makes the switch an example of what are sometimes called higher-order quantum processes. Instead of merely transforming a quantum state, the larger process takes quantum operations themselves and arranges how they act. You can think of an ordinary operation as a machine that accepts a quantum system and returns a changed quantum system. A higher-order process takes machines of that kind as inputs and determines how they are used. The quantum switch uses this extra level to control the order in which two operations are encountered. This sounds abstract, but it provides a clean way to separate two questions that ordinary circuits normally merge together. What operations are performed, and in what causal order are they performed? Once those questions are separated, researchers can ask whether indefinite order offers practical advantages. In several theoretical information processing tasks, processes involving the quantum switch can use operations differently, from strategies restricted to a fixed causal order. Certain problems involving distinguishing quantum operations, communication through noisy processes, and other information tasks can benefit from coherent control of order. These results matter because they show that indefinite order is not simply a new vocabulary for an old arrangement. When the ordering structure itself is used as a quantum resource, it can affect what can be accomplished with the available operations. Recent theoretical work has continued to study differences between the quantum switch and conventional fixed-order quantum circuits, including situations where simulating the switch with ordinary circuits can require additional uses of the available operations. Even here, care is needed. There is more than one level of claim hiding inside the phrase indefinite causal order. A quantum switch can have what physicists call a causally non-separable structure, meaning that the process cannot simply be written as an ordinary probabilistic mixture of one causal order and the reverse order. That does not automatically mean every imaginable test of causal order will show a violation. There are stronger forms of causal indefiniteness associated with special constraints known as causal inequalities. The quantum switch occupies a subtler position. It challenges fixed classical ordering without turning the laboratory into a place where unrestricted signals can loop through time. This is one of the reasons careful experimental tests remain important. Experiments have implemented versions of the quantum switch using optical systems and other quantum platforms, and researchers have developed tests intended to distinguish coherent control of order from ordinary fixed-order explanations. The experimental interpretation can depend on assumptions about how the device's paths and control systems are modelled, so physicists have continued working on ways to reduce possible loopholes. A recent experimental effort reported in 2026 was specifically designed to strengthen the evidence for a superposition of orders while acknowledging that some assumptions still remain. That continuing work is a useful reminder that the field is not claiming more certainty than the experiments support. The phenomenon is serious enough to test carefully precisely because the conceptual claim is so unusual. It also helps to separate indefinite causal order from faster-than-light communication. The two ideas are often pushed together because both sound like challenges to ordinary causal intuition, but they are not the same. The quantum switch does not allow someone to send a controllable message into their own past. It does not create an ordinary communication channel in which an answer arrives before the question is asked. It does not provide a method for violating the familiar relativistic restriction that usable information cannot simply be transmitted faster than light through ordinary space-time. The unusual feature concerns how operations are organized inside the quantum process. Physics remains constrained. The strange part is that the constraints need not look like one fixed classical sequence. This makes indefinite order very different from the usual science fiction picture of causality breaking down. In fiction, a causal paradox often involves a person travelling backward through time and preventing an event that was necessary for the journey to happen. The contradiction comes from placing ordinary objects inside a loop of ordinary causes and effects. Quantum indefinite order is not that. There is no traveller meeting an earlier version of themselves. There is no event deleting its own cause. There is no requirement that an outcome both happen and fail to happen. The quantum process remains mathematically consistent. What disappears is not logic, but the demand that every relevant operation must sit inside one classical before and after arrangement. The distinction becomes easier to appreciate if we imagine two chefs rather than two quantum devices, while remembering that real chefs are far too large and environmentally noisy to display the effect. Suppose one chef adds an ingredient and another chef heats the mixture. In one ordinary order, the ingredient is added before heating. In the reverse order, the mixture is heated before the ingredient is added. We can randomly choose between these procedures, but every cake still has one preparation history. A genuinely quantum version would require the two orders to remain coherent so that they could later interfere. There would be no ordinary hidden notebook in which nature had quietly written down the one sequence that really happened. The final outcome could depend on the relationship between both possibilities. Real kitchens thankfully do not behave this way, which is just as well because recipes are already difficult enough when someone writes a teaspoon as a tablespoon. The analogy also reveals why environmental isolation matters so much. A chef leaves enormous records. Heat spreads through the room, ingredients move, light reflects from every surface, air molecules collide with everything. Other people can watch. These interactions make the sequence overwhelmingly definite. A carefully controlled quantum system can avoid leaving enough distinguishing information for the alternatives to become classical. The experiment must preserve the possibility that the different orders remain coherent until they are recombined. The moment the environment obtains reliable information that distinguishes one order from the other, the delicate quantum relationship becomes harder to observe. This gives us another clue about why causal order might appear fundamental even if it is not. Our world is full of systems constantly leaking information into their surroundings. Macroscopic events produce records almost immediately. Those records make alternative histories distinguishable. Once that happens, one sequence becomes effectively fixed for every practical observer. You can inspect the environment and reconstruct what occurred. At the quantum level, however, if the information distinguishing different sequences has not escaped, the alternatives can remain part of one coherent process. Definite causal order may therefore be something the environment continually helps create. There is a subtle danger in saying that the environment creates the order, because that can sound as though nothing happened until someone looked. That is not what is required. The environment itself consists of physical systems. A stray photon can carry distinguishing information whether or not any person ever detects it. An air molecule can become correlated with a quantum system without anyone knowing. Decoherence is not an act of human attention. It is an ordinary physical interaction. Once enough information about the alternatives spreads into uncontrollable surroundings, interference between them becomes effectively inaccessible. A stable classical history emerges without a conscious observer having to choose it. The quantum switch therefore sits at an interesting boundary. It uses ordinary laboratory equipment to preserve a feature that ordinary environments normally erase. At the beginning and end of the experiment, researchers deal with classical records. They prepare settings, operate devices, and collect definite measurement results. Between those points, the quantum process can resist being described by one fixed ordering. The experiment is not a second universe with different laws. It is our universe operating in a regime where a familiar macroscopic assumption is no longer compulsory. This raises a deeper question about what causal order actually belongs to. We usually imagine that events have causal relations because they occupy positions in spacetime. One event happens here, another happens there, and the geometry tells us whether influence could travel between them. In the quantum switch, however, physicists can discuss indefinite operational order without requiring space-time itself to become wildly distorted. That suggests causal order is a richer concept than simply reading timestamps from clocks. The ordering of quantum transformations can have a structure of its own. At the same time, we should resist concluding that the quantum switch has already proved space-time itself is indefinite. It has not. Experiments involving coherent control of operation order are not the same as directly placing space-time geometry into a quantum superposition. That more ambitious possibility belongs to quantum gravity, where mass, geometry, and causal structure may all have to be treated quantum mechanically. The switch is valuable because it teaches us how to think about a world in which causal structure need not always be fixed, and it provides laboratory tools for studying that idea without requiring access to black holes or impossibly strong gravitational fields. There is another important lesson in the fact that indefinite order can be useful. Physics often becomes more confident that an unusual concept is meaningful when the concept does work. Quantum entanglement was once treated as an unsettling conceptual feature of quantum theory. Today it is also a resource used in quantum information. Superposition is not merely a philosophical puzzle, it is used in sensing, communication, and computing. In the same spirit, if coherent control of causal order enables tasks that fixed order processes cannot perform in the same way, then causal indefiniteness becomes something we can treat operationally, rather than only discuss at a philosophical distance. Research on the quantum switch has explored advantages in areas including communication and processing quantum information, while also studying how fragile the effect can be when the control system interacts with an environment. That fragility is exactly what we should expect from the story we have already built. The moment the control loses the coherence connecting the alternative orders, the special interference between them is reduced. Environmental noise pushes the process back towards something that can be understood as ordinary alternatives rather than one coherent, indefinite ordering. Work studying these environmental effects shows how the transition from quantum causal structure toward familiar definite order can be approached as a physical process rather than a vague philosophical change. This may be one of the most useful ways to think about emergence in this context. We do not need to imagine that the universe has two completely separate sets of laws, one bizarre set for tiny particles and one sensible set for cups and planets. The same quantum framework can produce different effective descriptions depending on how strongly systems interact with their environments. Preserve coherence and unusual alternatives remain available. Allow the environment to record which alternative occurred, and the process behaves increasingly classically. At our scale, the recording happens constantly and overwhelmingly, so definite histories appear natural. If causal order follows the same pattern, then the question of which event came first may sometimes have a definite answer, because the physical situation has made the alternatives distinguishable, not because reality required that answer at every deeper level. This is a subtle change in perspective. Instead of starting with a universal sequence and placing quantum events inside it, we allow the possibility that definite sequences are among the structures produced when quantum relationships become sufficiently stable and classical. The idea becomes more interesting when we ask whether order can be indefinite without producing contradictions. Everyday intuition tells us that if neither operation is definitely first, then each must somehow depend on the other, creating a circular problem. Quantum mechanics avoids this because indefinite order does not require ordinary two-way signalling. It is not a pair of classical events each waiting for the other to happen. The entire process is described as one quantum object, with alternative orderings contained within it. Trying to break that object into a conventional story can create the impression of a paradox that is not present in the actual theory. This is similar to other areas of quantum mechanics, where insisting on a classical story causes trouble. Ask which slit a particle definitely passed through in an interference experiment, and you may be demanding information the coherent experiment was specifically designed not to provide. Ask which member of an entangled pair carried the hidden instruction responsible for a correlation, and experiments tell us that simple, local hidden explanations are not enough. Ask which of two quantum operations definitely happened first in a genuinely coherent ordering, and again the classical question may be demanding a fact that the process does not possess in the expected form. There is something important in that pattern. Quantum mechanics repeatedly warns us that possibilities do not always need to become classical facts before they participate in physical behaviour. A path can matter without being one definite classical trajectory. A measurement outcome can remain part of a superposition before a record forms. An entangled system can possess relationships that cannot be reduced to independent local properties. Causal order may be another item on that list. The relationship called first and second can matter without having been assigned one fixed classical value throughout the process. At this point, the original picture of causality is shifted considerably. We began with the simple assumption that causes happen first and effects follow. We then found that relativity already limits the idea of universal temporal order. Quantum mechanics allows physical alternatives to remain coherent. Carefully controlled processes can extend that coherence to alternative orders of operations. Decoherence explains why such possibilities disappear from ordinary experience. None of this abolishes causal reasoning, but it makes causality look less like a rigid background and more like a structure that may have different forms in different physical regimes. The question waiting underneath all of this is what produces the direction we associate with cause and effect. Indefinite causal order shows that a fixed sequence may not always be necessary, but our ordinary world still has an unmistakable temporal orientation. We remember one direction and anticipate the other. Information leaves records behind us rather than ahead of us. Broken glasses remain broken, heat spreads, measurements create stable records. Whatever quantum possibilities exist underneath, the world we inhabit overwhelmingly distinguishes past from future. That means causal order cannot be understood fully by looking at ordering alone. We also need to understand the relationships that quantum systems can possess across space and time, and why those relationships do not automatically behave like ordinary signals moving from one event to another. Entanglement becomes especially important here because it shows that nature can contain remarkably strong connections without fitting them into the familiar picture of one object simply sending an influence to another. Once those connections are placed alongside the thermodynamic direction of time, the question changes again. Instead of asking only which event comes first, we have to ask why any direction of cause appears so definite in a quantum universe where the underlying relationships can be much less local and much less sequential than everyday experience suggests. Entanglement is a useful place to continue because it forces us to separate two ideas that everyday experience usually keeps together. The first is correlation, the fact that two events or two systems are related in a reliable way. The second is causation, the claim that one of those events produced or influenced the other. In ordinary life, strong correlations often tempt us toward causal explanations. You hear the sound of a glass breaking and then discover fragments on the kitchen floor. The sound and the broken glass are related because both came from the same physical event. You turn a key and the engine starts. The two events are related because the first participates in producing the second. Most of the time, the distinction is manageable because information seems to move through a clear sequence. Quantum entanglement makes that comfortable picture much harder to maintain. Two entangled systems can display correlations that are stronger and stranger than anything we can explain by imagining each system carrying a complete set of ordinary hidden instructions from the beginning. Yet those correlations still cannot be used as a normal signal sent from one system to the other. Something is connected, but the connection refuses to behave like a familiar chain of cause followed by effect. Imagine two quantum systems prepared together and then moved far apart. Later, measurements are performed on each of them. Quantum mechanics predicts relationships between the results that depend on how the measurements are chosen. The correlations can be so strong that a simple classical story does not work. We cannot explain everything by saying that each system left the source with a private list of predetermined answers and merely revealed the appropriate one when measured. Experiments have repeatedly supported the quantum predictions rather than that simple local hidden instruction picture. This does not mean one measurement sends a controllable message instantly to the other. If you look only at the results available on one side, they appear random. The striking pattern becomes visible when the two sets of results are later compared. That detail matters enormously because it prevents entanglement from becoming an ordinary faster-than-light telephone. The systems are related in a way that classical intuition struggles to represent, but the relationship does not behave like a signal racing from one detector to another. Our everyday instinct immediately wants to ask which measurement affected which. If the result on one side is connected to the result on the other, perhaps one must have happened first and caused the second. That is a natural question, but relativity makes it difficult to maintain as a universal explanation. If the two measurements occur far enough apart that no ordinary signal travelling at or below the speed of light could connect them, different observers can disagree about their temporal order. One observer may describe the first measurement as happening before the second. Another observer moving differently may describe the second as happening before the first. If the correlation required one particular measurement to be the cause and the other to be the effect, physics would have to choose one observer's ordering as physically privileged. Relativity gives us no ordinary reason to do that. The quantum correlation therefore sits in an unusual category. It is real and measurable, but it is not naturally described as a simple message travelling from the earlier measurement to the later one. This is one of the reasons entanglement is so important when thinking about whether causality is fundamental. It shows that nature can contain relationships that are more basic than the causal stories we instinctively build around them. Two outcomes can belong to one larger quantum structure, even when it is misleading to imagine one outcome producing the other. The joint state carries the relationship. When measurements are later compared, the structure becomes visible through the statistics. Instead of picturing two separate objects exchanging an invisible instruction at the moment of measurement, it is often more accurate to think of the pair as parts of one quantum system whose properties cannot always be divided into independent local pieces. That does not eliminate causality. The preparation of the entangled system still matters. The measurement choices matter. Physical interactions still obey strict constraints. What changes is the idea that every correlation must be explained by a direct causal arrow running between the correlated events. Sometimes two events are related because they share a common origin. Sometimes they are related because one influences the other. Quantum mechanics adds correlations that resist simple classical explanations of either kind. The temptation to force them into an ordinary causal chain can create more confusion than understanding. There's another reason the subject becomes difficult, and that is our habit of imagining time as a sequence of moments being created one after another. If reality unfolds in that way, then every correlation seems to demand a story about how information moved from an earlier moment into a later one. Yet relativity already taught us that the universe does not contain one universal presence shared by everyone. The division between past, present and future depends partly on the observer, while causal relationships are preserved only where physical influence can actually connect events. Entanglement adds a second warning. Some quantum relationships do not fit comfortably into the picture of properties being carried locally from one moment to the next. This becomes especially interesting when physicists ask whether entanglement could help explain spacetime itself. Several approaches to quantum gravity have suggested deep connections between patterns of quantum entanglement and the geometry that appears at larger scales. The details vary from one theoretical framework to another, and no complete experimentally confirmed account has settled the issue, but the general idea is worth understanding. Instead of assuming that quantum systems sit inside an already existing space-time, perhaps some features of space-time arise from how deeper quantum degrees of freedom are related. In that kind of picture, distance and geometry may reflect patterns in the underlying quantum structure. If space-time emerges, then the causal relationships normally defined by space-time may emerge as well. This reverses the order in which we usually explain things. We normally begin with space and time, place objects inside them, and then ask how those objects influence one another. An emergent space-time picture asks whether the relationships come first in the description, and whether the familiar stage of space and time appears only afterward. If that is even partly correct, causality would no longer have to be the foundation upon which quantum relationships are built. Quantum relationships might instead help produce the structure in which definite causal order becomes meaningful. Entanglement also complicates the way we think about temporal direction, because the basic quantum correlations themselves do not obviously contain the everyday distinction between cause and consequence. Suppose two systems interact and become entangled. Later, they separate. We can describe the joint quantum state and calculate correlations between measurements. The equations give us relationships among possible outcomes, but our experience adds a narrative. We say the systems interacted earlier, the correlation was established, and the later measurements revealed it. That narrative is perfectly useful, especially in the laboratory, but the deeper formal structure often focuses on relations between physical states, rather than on a story in which one measurement creates the other result. Why, then, does our world have such a strong direction of cause at all? Why do we not experience causality as a collection of neutral relationships with no preferred orientation? The answer seems to involve something larger than entanglement alone. It brings us back to the thermodynamic arrow of time. The microscopic laws underlying many physical processes are far more reversible than everyday events appear. If you watched a simple collision between a few idealized particles and then played the process backward, the reversed motion could still be consistent with the basic physical laws. Yet a glass shattering on the floor looks obviously different when reversed. Smoke spreading through a room looks normal in one temporal direction and absurd in the other. A warm drink cools toward room temperature, while a room does not normally coordinate its molecular motion to heat one particular forgotten cup of tea. The difference comes from the behavior of huge numbers of microscopic components. Macroscopic systems overwhelmingly move from special arrangements toward more common arrangements. Energy spreads. Information becomes distributed among more degrees of freedom. Entropy tends to increase. This gives the large-scale world a preferred temporal direction, even when many of the microscopic interactions do not contain such an obvious preference. The past is associated with lower entropy conditions and the future with higher entropy conditions, at least in the ordinary processes around us. Causal direction appears to align with this thermodynamic direction. Causes tend to leave records in their effects. An event happens and information about it spreads outward. A stone hits a window, producing fragments, sound waves, vibrations, scattered light, and perhaps an unpleasant conversation about replacement costs. Each consequence contains some information about the collision. The later environment holds many traces of the earlier event. Reverse the story and the arrangement becomes fantastically unlikely. The scattered fragments, sound waves, vibrations, and light would all have to coordinate themselves so that they converged on one location and reconstructed the impact. This spreading of information helps explain why we can infer causes from effects. Present conditions contain records of earlier events. Fossils contain information about organisms that lived long ago. Light reaching a telescope contains information about distant stars as they were when the light began its journey. A scar contains information about an earlier injury. Your memory of breakfast is a physical record created by processes in your brain. The world is filled with systems that preserve traces of what occurred in the direction we call the past. The opposite arrangement is missing. We do not possess ordinary physical records of future events. There is no photograph on your desk showing tomorrow's breakfast. In the same way, there may be a photograph of yesterday's dinner. Your brain contains memories of earlier experiences but not later ones. This asymmetry is so universal in ordinary life that we build our entire concept of causation around it. A cause belongs to the side of time from which records arrive. An effect belongs to the side where new records are created. Entanglement fits into this picture in an interesting way because entanglement itself can grow as systems interact. A small quantum system becomes correlated with its environment. The environment then interacts with more systems. Information that was initially contained in a delicate local relationship becomes distributed across many degrees of freedom. This process is closely related to decoherence, the same mechanism that makes large objects appear classical. As entanglement with the environment grows, quantum alternatives that could once interfere become effectively inaccessible. Stable records appear. A definite macroscopic history becomes the useful description. Seen this way, the arrow of cause may be connected to the direction in which quantum information becomes distributed. Earlier events influence many later degrees of freedom, because their information spreads outward through interactions. Later events do not ordinarily reconstruct the earlier concentrated quantum state, because doing so would require an extraordinary reversal of those correlations. The direction of causation we experience may therefore depend partly on the direction in which entanglement and entropy typically grow in the world around us. This does not mean physicists have reduced causality to one simple statement about entanglement. The connection is more complicated than that. Entanglement can increase, decrease, be redistributed, or be manipulated in carefully controlled systems. Entropy itself has several meanings depending on the physical context. The full relationship between quantum information, thermodynamics, spacetime, and causal order remains an active area of theoretical research. The important point for our discussion is that the direction of cause may not need to be inserted into every microscopic interaction as a separate fundamental rule. It could arise because large systems begin in special conditions and evolve in a way that creates records, spreads correlations, and makes one temporal direction overwhelmingly different from the other. This possibility also explains why the arrow of cause feels so absolute to us. We are not neutral observers hovering outside thermodynamics. Our bodies depend on irreversible processes. We consume energy, release heat, create memories, repair tissues, and constantly interact with the environment. Thinking itself involves physical changes in the brain. Every memory you form is part of the same universe in which information becomes recorded and entropy tends to increase. Your experience of time is therefore tied to the physical arrow you're trying to understand. Imagine a hypothetical observer whose memory worked in the opposite thermodynamic direction. Such an observer is difficult even to define because memory requires physical records. To remember what we call the future, the observer's present state would somehow need to contain reliable information about events that, from our perspective, have not yet left those records. Building a consistent physical model of such an observer is not as simple as reversing a film. The observer, their environment, their memories, and all of the thermodynamic processes supporting them would have to be treated together. The fact that this is so difficult reminds us that the psychological arrow and the thermodynamic arrow are not independent accidents. They appear deeply connected. Causality then becomes part of a larger package. We remember earlier events. Those memories are records. Records exist because physical interactions spread information. The spreading is associated with thermodynamic irreversibility. We use those records to infer causes. We use present conditions to predict later effects. From inside this structure, cause before effect feels unavoidable. Yet the microscopic laws may not contain the same sharply directed distinction. Entanglement gives us an especially clear example of why the deeper description may involve relations rather than arrows. Consider the correlations between two entangled measurements again. From the perspective of one observer, one measurement may occur first. From another valid perspective, the other measurement may occur first. The quantum prediction does not depend on assigning one of those measurements the role of universal cause. What matters is the joint structure of the experiment. The correlation belongs to the pair rather than being delivered from one result to the other. This is very different from ordinary causal influence. Suppose you send a letter. The letter is written first, transported and received later. Everyone agrees that the receipt depends on the earlier sending because a physical object carries information through spacetime. The causal path is clear. Entanglement correlations do not work this way. There is no controllable message hidden in one result and transmitted instantly to the other. Each local outcome is not something the experimenter can choose. Only after the results are brought together does the correlation become visible. That difference is exactly why entanglement can coexist with relativity. If one observer says one measurement happened first, and another says the reverse, neither description allows a paradox because neither measurement can be used to control the distant result in the way an ordinary signal controls a receiver. There is a relationship without the kind of directional influence that would force one universal temporal order. This suggests that correlation may be more basic than causation, in at least some quantum descriptions. Causation adds direction and the possibility of intervention. A cause is not merely associated with an effect. Changing the cause should, under appropriate conditions, change the effect. Entangled correlations are not that simple, because choosing a local measurement does not give you direct control over the distant outcome. The relationship is real, but it does not behave like a classical mechanism. Some physicists and philosophers therefore distinguish carefully between causal explanation and structural explanation. A causal explanation tells us what produced what. A structural explanation tells us how parts of a system are related within a larger whole. Quantum mechanics often seems comfortable with the second kind. The state of a composite system can encode relationships that cannot be assigned separately to the parts. From that perspective, asking which part caused the other may be the wrong question. This becomes even more interesting if the block universe view of spacetime is considered. In a block universe, the entire spacetime history is represented as one four-dimensional structure. Events do not need to be imagined as popping into existence one after another as a universal present advances. Earlier and later, events are simply located differently within the space-time structure. Causal relationships still exist because space-time limits, which events can influence others, but the picture of the past continually manufacturing the future becomes less obvious. Combine that with entanglement, and the universe begins to look less like a machine, passing instructions forward one moment at a time and more like a network of relationships constrained across a larger structure. This does not prove the block universe interpretation is the final answer, and it certainly does not prove that causes are unreal. It simply shows that modern physics offers ways of describing reality in which directional causal stories are not always the most fundamental language available. There are also interpretations of quantum mechanics that go further and explore whether later measurement settings can participate in the description of earlier quantum events. These are often called retrocausal approaches. The word immediately suggests science fiction, but the actual proposals are usually much more restrained. They do not necessarily allow anyone to change an event that already happened or send a useful message into yesterday. Instead, they question whether quantum states should always be understood using conditions from the past alone. Perhaps both earlier preparation and later measurement conditions participate in determining the complete description of what lies between them. Entanglement is one of the reasons such ideas are considered at all. If quantum correlations resist a simple story of local influences moving forward through time, perhaps the structure is better understood using constraints that involve both ends of an experiment. Whether this is the correct interpretation remains unsettled. Standard quantum mechanics works extraordinarily well without requiring everyone to adopt a retrocausal picture. The point is that once ordinary forward causal explanation becomes difficult, other ways of organizing the same experimental facts become possible. None of this changes what happens when you push a cup across a table. The push occurs before the cup moves in response. Information and momentum pass through an ordinary physical interaction. The event leaves records. Decoherence suppresses quantum alternatives. Thermodynamics supplies a stable temporal direction. Your brain remembers the push and sees the later movement. Every relevant layer agrees on the same causal story. That is why everyday causation remains so dependable. The deeper lesson is not that causality fails, it is that several different physical ingredients cooperate to make causality look as fundamental as it does. Relativistic spacetime provides limits on influence. Quantum interactions create correlations. Decoherence selects stable macroscopic histories. Thermodynamics gives those histories a direction. Memory records one side of that direction. Living organisms learn to use the resulting regularities for prediction. By the time all of these ingredients are combined, cause before effect seems like the most obvious rule imaginable. Remove some of those ingredients, and the picture changes. Isolate quantum systems and coherent alternatives return. Separate entangled systems and correlations appear without ordinary signals. Control different operation orders quantum mechanically, and definite sequence can become unnecessary. Consider theories in which space-time itself emerges, and even the causal structure may no longer be the starting point. What looked like one simple law begins to resemble the combined result of several deeper structures. This makes the arrow of cause less like an arrow painted onto every fundamental event, and more like a direction that becomes visible once the universe is viewed at the scale where records, entropy, memory, and classical space-time all line up. The arrow is completely real for us because we live inside the conditions that create it. The open question is whether the deepest level of reality contains that same arrow, or whether it contains relationships from which the arrow emerges. That question becomes especially difficult when we stop insisting that explanation must always begin in the past. Quantum mechanics allows us to calculate correlations between preparations and measurements without always telling one unique story about what physically happened between them. Some interpretations preserve a strictly forward causal picture. Others treat the entire experiment more symmetrically. A few allow later conditions to play a role in how earlier quantum states are described. None of these approaches gives us a practical machine for rewriting history, but they force us to ask whether our insistence that influence must always point from past to future comes from fundamental physics or from the particular large-scale conditions in which human observers happen to exist. That is where the next step becomes unavoidable, because once the direction of cause is no longer assumed from the beginning, we have to confront the possibility that what happens later might belong to the explanation of what happened earlier, without producing the paradoxes we normally associate with changing the past. Once we allow ourselves to question whether causal direction is fundamental, one possibility appears almost immediately, and it is usually the one that makes people sit up a little straighter. Could the future influence the past? The idea sounds dangerous because ordinary causality seems to depend on exactly the opposite rule. You decide to make tea, then you boil the water. You send a message, then someone receives it. You drop a book, then it hits the floor. We never seem to encounter an event whose cause is waiting several minutes ahead of it. If that happened routinely, everyday life would become extremely difficult to organise. You might hear the doorbell because someone was going to press it tomorrow, receive a reply before writing the email, or discover that tonight's dinner had somehow caused yesterday's trip to the supermarket. Nothing like this happens in ordinary experience, and no accepted quantum experiment allows us to send usable information into our own past. That point needs to remain clear from the beginning. The interesting question is more restrained. Perhaps some quantum processes can be described in a way where later conditions help determine the complete physical relationship connecting earlier and later events, even though nobody can use that relationship to rewrite history or send a warning to yesterday. The distinction matters because influence can mean several different things. In everyday conversation, saying that the future influences the past usually suggests that something happens tomorrow and reaches backward to alter something that already occurred today. That creates immediate logical problems. Suppose you receive a note from tomorrow telling you not to send the note. You obey it, so tomorrow you never send it. Now there is no note to receive, so perhaps you do send it after all. Very quickly we have left physics and entered the sort of afternoon normally occupied by time travel films. Retrocausal approaches to quantum mechanics generally do not require this kind of editable history. They are attempts to understand quantum correlations by treating the boundary conditions of an experiment more symmetrically. Instead of assuming that only the preparation in the past contributes to the complete description of a quantum system, some approaches ask whether the later measurement context might also matter to that description. To see why anyone would consider such an idea, remember the difficulty we encountered with entanglement. Two entangled systems can display correlations that are difficult to explain using ordinary local causal stories. We cannot simply imagine each system leaving the source with a complete hidden list of predetermined answers. Experiments rule out broad classes of those local hidden variable explanations. Yet we also cannot use the correlations as an ordinary faster-than-light communication channel. The relationship is real, but it does not behave like a message being sent from one detector to another. This leaves us with several ways to think about what the theory is telling us. One option is simply to accept the quantum formalism and avoid insisting on a detailed underlying story. Another is to adopt an interpretation in which the quantum state branches, collapses, or represents information in a particular way. Retrocausal approaches explore a different possibility. Perhaps the assumption that all relevant physical influence must originate in the past is doing more work than we realized. Imagine a quantum experiment in which a system is prepared in one way at the beginning and measured in another way at the end. In the ordinary forward-looking description, the preparation establishes the initial quantum state. The state then evolves until the later measurement, which produces an outcome according to the quantum probabilities. That picture treats the past as the source of information, and the future as the place where consequences appear. A time-symmetric description asks whether this asymmetry is truly required by the underlying physics. Perhaps the complete description of the period between preparation and measurement should depend on information from both boundaries. The earlier preparation constrains what can happen from one direction, while the later measurement constrains it from the other. This does not necessarily mean anything travels backward through time in the ordinary sense. A constraint is not always the same thing as a signal. Consider a completed crossword puzzle. A letter in the middle may be constrained by a word running from left to right, and another word running from top to bottom. Neither word needs to send a message to the other. The solution is determined by the compatibility of the whole structure. Something roughly similar motivates some time-symmetric ways of thinking about quantum theory. Instead of imagining reality being calculated step by step from the past alone, the physical history between two events might be constrained by conditions at both ends. There is a formal approach to quantum mechanics known as the two-state vector formalism that develops this time-symmetric perspective. In this description, an ordinary state evolving from an earlier preparation is supplemented by information associated with a later selection or measurement. The system between those boundaries is then described using both. This does not change the experimentally confirmed predictions of standard quantum mechanics in the situations where the approaches are equivalent. It changes the conceptual organization of the description. The earlier condition is no longer the only boundary that matters. The temptation is to translate this immediately into a little movie in which a mysterious influence travels backward from the detector toward the source. Some interpretations do use language that sounds something like that, but the safer lesson is that time-symmetric quantum models do not have to treat past conditions as uniquely privileged. The complete relationship between preparation and measurement can be considered as a whole. That sounds less dramatic than changing the past, but it is conceptually significant. If fundamental physics can be expressed without insisting that explanation always runs from earlier conditions toward later ones, then the arrow of causation we experience may be something added by the macroscopic world, rather than something demanded by the deepest quantum description. This becomes especially interesting when we look at delayed choice experiments. These experiments are famous partly because their names seem designed to cause unnecessary anxiety. A quantum system begins travelling through an apparatus, and the experimental arrangement that determines what kind of information can later be obtained may be chosen only after the system has already entered, or in some versions passed through, an earlier portion of the experiment. The results agree with quantum mechanics, but ordinary language makes the situation sound suspicious. If the later choice affects which type of pattern appears in the completed data, did the future choice determine what the particle was doing earlier? The answer from standard quantum mechanics does not require us to say that a completed past event was physically rewritten. The trouble usually begins when we insist that the quantum system must have possessed one definite classical history before the entire measurement arrangement was taken into account. We imagine the photon secretly deciding to behave in one familiar way at an earlier moment, then imagine the later experimental choice somehow forcing that earlier decision to change. Quantum theory does not require that first classical story. If the relevant property did not have one definite classical value in the way we assumed, there is nothing that needs to travel backward and edit it. The delayed choice quantum eraser makes this especially easy to misunderstand. In common retellings, one photon appears to produce a result first, while a later measurement performed on an entangled partner seems to decide whether the earlier photon behaved as though path information existed, or as though interference existed. This can sound like the later experiment reaches into the past and changes the earlier detection, but the earlier detector record itself does not transform after the later measurement. The full interference-related structure appears only when the earlier and later records are grouped and compared according to their correlations. You cannot stand beside the first detector, inspect its local results, and discover a message telling you which later measurement choice will be made. The usable pattern is in the joint correlations, not in a retroactively modified local record. Analyses of delayed choice quantum eraser experiments therefore do not require backward communication or a rewritten past. This is an important example because it shows how easily correlation can be mistaken for influence. Suppose you have a large collection of paired records. Only after sorting them according to another variable do two different patterns become visible. It is tempting to imagine that the later sorting created the earlier data, but the data were already there. The later information reveals how the records are related. Quantum mechanics makes the correlations more unusual than an ordinary sorting exercise, but the logical warning remains useful. Learning a relationship later does not automatically mean the later event physically caused the earlier event. Retrocausal interpretations go beyond this modest observation. They ask whether a deeper model of quantum mechanics might actually become simpler if influences or constraints were allowed to operate in both temporal directions. One motivation comes from the strange correlations we discussed earlier. If two distant entangled measurements cannot be explained using ordinary local variables travelling forward from a shared past, perhaps the restriction to forward influence is the problem. A later measurement setting might influence properties associated with an earlier common region, which could then help account for correlations without requiring a direct faster-than-light signal between the distant measurements. Picture 2 entangled particles moving away from a common source. Much later, two experimenters independently choose how to measure them. In the ordinary local causal picture, the source lies in the past of both measurements, so any hidden information carried by the particles would have to leave the source before the measurement choices were made. Bell-type experiments show that simple local hidden variable models of that kind cannot reproduce all the observed quantum correlations. A retrocausal model can consider a different arrangement. The later measurement choices could participate in determining the hidden physical description closer to the source. The correlations would then not require a signal shooting instantly across space from one measurement station to the other. Instead, the causal structure would include influences extending backward toward the shared past and then forward again. That sounds almost like a message being sent backward, but there is a major restriction. The experimenters still cannot control the individual quantum outcomes in the way required for useful communication. You cannot choose a measurement tomorrow and use that choice to make a readable sentence appear on a detector today. If you could, the world would look dramatically different, and the usual causal paradoxes would become difficult to avoid. Retrocausal models are constructed precisely so that the underlying time-symmetric relationships do not become an ordinary signalling channel into the past. This creates a strange distinction between underlying influence and observable control. At the deeper theoretical level, later conditions might participate in determining earlier hidden variables or intermediate descriptions. At the level available to experimenters, however, the statistics prevent anyone from using that dependence as a telephone to yesterday. You can influence the structure without gaining the power to choose the individual record that appears in the past. Whether this should truly be called causation depends partly on what one means by causation, which is one reason the subject remains debated. There is also a philosophical advantage that attracts some researchers to retrocausal ideas. The basic laws of physics often display more time symmetry than our everyday causal reasoning does. If a theory treats the past and future differently, we can reasonably ask where that difference comes from. Perhaps it is fundamental. Perhaps quantum measurement introduces a genuine asymmetry. Or perhaps the underlying laws are time-symmetric, while the asymmetry we experience comes from thermodynamic conditions, records, and the low entropy past we discussed earlier. A retrocausal model explores the possibility that quantum foundations should respect that deeper symmetry, rather than placing the entire burden of explanation on earlier conditions. Think again about a simple collision between microscopic particles. If the fundamental equations can describe the process consistently in either temporal direction, it is not immediately obvious why the interpretation of those equations must allow influences only from what we call past to what we call future. Our ordinary answer is that causes precede effects because that is how the world behaves. Yet much of that behaviour may come from thermodynamics. We remember one direction. Records accumulate in one direction. Large-scale processes become effectively irreversible in one direction. Those facts may explain the causal arrow without requiring every microscopic relation to carry the same orientation. There is a useful analogy in classical physics that avoids quantum mechanics entirely. Imagine a rope fixed at both ends. The shape of the rope is constrained by conditions at the left boundary and the right boundary. You can solve for the shape using information from both ends without saying that the right end travelled backward through space to cause the middle of the rope. The complete configuration satisfies a set of conditions simultaneously. Some approaches to fundamental physics ask whether histories through time might be treated in a similarly global way. Initial conditions and final conditions could jointly constrain the physical structure between them. Our ordinary experience hides this possibility because we know far more about the past than the future. We have photographs, memories, fossils, documents, scars, recordings, and millions of other traces left by earlier events. We do not possess comparable records from tomorrow. As a result, we naturally formulate physics as an initial value problem. Tell us the present state, apply the laws, and calculate what happens next. This method works extraordinarily well, but its practical success does not necessarily prove that reality itself is fundamentally constructed one instant at a time. A completed space-time description from relativity already encourages a different viewpoint. In the block universe picture, the history of space-time can be represented as a whole. Earlier and later events occupy different regions of the four-dimensional structure. From that perspective, asking whether the past creates the future can become less straightforward. Both belong to the structure. Causal relationships still distinguish which events can influence others, but the entire history does not need to be imagined as physically coming into existence one slice at a time. Add a time-symmetric quantum interpretation, and the picture becomes even less like the ordinary chain of dominoes. Instead of the past continually sending instructions toward an unwritten future, the universe might be describable through relationships spanning extended regions of space-time. What we call causes and effects could then be directional features of those relationships as seen from inside a world with a strong thermodynamic arrow. This does not mean every physicist accepts retrocausality. Far from it. Quantum mechanics has many interpretations, and they differ substantially in what they claim about reality between preparation and measurement. Some researchers regard retrocausal models as promising because they may offer new ways to understand quantum non-locality and time symmetry. Others believe they introduce conceptual problems without providing enough additional explanatory value. The experimental predictions are often shared with other interpretations, which makes deciding between them difficult. Retrocausality remains a serious possibility within quantum foundations, not an established discovery that the future literally controls the past. There is another approach known as the transactional interpretation that uses a particularly vivid time-symmetric language. In simplified descriptions, quantum processes involve waves associated with forward and backward temporal directions, combining into a completed transaction. This can make entangled or delayed choice experiments feel less mysterious, because the entire process is treated as a relationship across space-time, rather than as a sequence in which a wave travels forward, suddenly collapses, and somehow coordinates distant outcomes. Yet even here, the interpretation does not provide a practical backward signaling device. A delayed choice quantum eraser, for example, still does not let an experimenter transmit a controllable message into the past. The inability to signal backward is more than an inconvenient technical limitation. It may be the reason retrocausal ideas can coexist with the world we experience. Imagine that microscopic relations were allowed to depend on both earlier and later boundary conditions, but the statistical structure always prevented macroscopic observers from controlling the information in the reverse direction. At the microscopic level, time could be treated more symmetrically. At the macroscopic level, thermodynamics and decoherence would still produce stable records pointing from past to future. We would experience exactly the familiar causal world, even though the underlying description was not entirely forward-directed. This would make the causal arrow another example of emergence. The deepest theory could contain time-symmetric relationships. Large systems would interact with enormous environments. Entanglement would spread. Information would become recorded. Entropy would increase toward what we call the future. Observers like us would form memories in that same direction. From inside the resulting macroscopic world, influence would appear to flow from remembered causes toward anticipated effects. We would have no access to any microscopic backward contribution as a controllable signal. There is something appealing about that possibility, because it allows the fundamental laws in the experienced world to have different kinds of symmetry without contradicting each other. A snowflake can have properties that no individual water molecule possesses. A fluid can flow even though no molecule is itself a flowing fluid. A biological organism can be alive even though its atoms are not individually alive. In the same spirit, a universe whose microscopic relationships are not fundamentally committed to one causal direction could still produce creatures who experience an extremely strong arrow of cause. There is also something uncomfortable about it. Our idea of explanation is built around the past. When someone asks why an event happened, we search backward. Why is the floor wet? Because the glass spilled. Why did the glass spill? Because someone knocked it. Why did they knock it? Perhaps because the cat appeared at exactly the wrong moment, thereby restoring the cat to its traditional role in examples of causality. We continue moving backward until we reach conditions that seem sufficient for the explanation. Saying that a later event might also participate in the explanation feels almost grammatically wrong, yet that reaction may tell us more about human experience than about fundamental physics. We evolved in a macroscopic environment where the thermodynamic arrow is overwhelming. Natural selection rewarded organisms that predicted future consequences from past patterns. A creature that waited for tomorrow to explain whether a predator was approaching would have a difficult career. Our brains became prediction machines operating in one temporal direction. It would be surprising if our intuition were perfectly suited to a microscopic world where the most useful description might treat temporal boundaries more symmetrically. There is one final distinction worth keeping firmly in place. A theory can be time-symmetric without being retrocausal, and an experiment can look retrocausal without actually requiring backward influence. These ideas are related but not identical. The fact that a physical law works similarly when time is reversed does not automatically mean effects cause their causes. Likewise, delayed choice experiments do not by themselves prove that later measurements rewrite earlier events. Retrocausality is an interpretive or theoretical proposal about how the relationships beneath quantum predictions might be organized. So could the future influence the past? Physics does not currently give us evidence that tomorrow can send controllable information into yesterday, and ordinary delayed choice experiments do not demonstrate a rewritten history. What modern quantum theory does give us is permission to ask a subtler question. Must the deepest explanation of a physical process always be constructed entirely from earlier conditions moving forward? Or could a complete description involve constraints extending from both temporal directions? That possibility changes the meaning of the original question. Instead of picturing the future reaching backward and rearranging an event that has already occurred, we can imagine that earlier and later events are parts of one larger physical structure whose internal relationships are not fully captured by the story of one moment producing the next. What looks like forward causation from inside the structure may be one effective way of reading relationships that are more symmetric when viewed as a whole. And once that possibility is taken seriously, an even larger question appears. Perhaps the real difficulty is not deciding whether influence travels forward or backward through space-time. Perhaps space-time itself is not the fundamental arena in which these relationships exist. If space, time, and causal order emerge together from deeper quantum connections, then asking whether the future influences the past may already assume more structure than the underlying theory contains. To understand that possibility, we have to move away from particles travelling through a pre-existing universe and consider a stranger idea, that the space-time separating causes from effects may itself be something produced by a deeper quantum network. That deeper quantum network is where the question becomes much more radical, because everything we have discussed so far has quietly assumed that events take place somewhere and at some time. Even when causal order became indefinite, even when entanglement connected distant systems in ways that resisted ordinary explanation, we still pictured a laboratory sitting inside space, clocks ticking on the walls, detectors occupying definite locations, and experiments unfolding against a space-time background that was simply there. But some approaches to fundamental physics ask us to remove even that background. They suggest that space and time may not be the basic stage on which reality happens. Instead, space-time itself may emerge from something deeper, perhaps from patterns of quantum relationships that do not initially look like locations, distances, or moments at all. If that possibility is correct, then cause and effect face an even greater challenge, because causal order is normally defined using space-time. We say one event can influence another because the structure of space-time allows a signal to travel between them. If space-time is not fundamental, then the familiar structure that tells us which event can cause which other event may not be fundamental either. This can be difficult to imagine because space feels like the most obvious thing in the world. You're somewhere right now. The device playing this video is some distance from the wall, the bed, the window, or whatever happens to be nearby. Objects have positions, rooms have sizes, cities are separated by distances, planets orbit stars across enormous regions of space. It feels absurd to ask whether space really exists, yet physics has often taught us that the properties most obvious at human scales do not always appear in the same form at deeper levels. A solid table feels continuous, but its microscopic description involves atoms and quantum fields. Temperature seems like a basic property of a cup of tea, but it emerges from the collective behaviour of enormous numbers of particles. A sound seems like one thing travelling through the air, yet it is produced by coordinated pressure changes involving countless molecules. The large-scale property is real, but it need not be fundamental. Space-time may work in a similar way. The idea does not mean that your room is imaginary, or that the distance between London and Tokyo will disappear if someone discovers the correct theory of quantum gravity. Emergence does not make something unreal. It means that the useful, large-scale structure may arise from more basic ingredients, whose own description looks very different. A wave is real even though no single water molecule contains the wave. A traffic jam is real even though no individual car is the traffic jam. A forest is real even though no single tree contains the forest. In the same way, space-time might be real as a large-scale structure without being one of the most basic ingredients in the universe. The reason physicists consider this possibility comes partly from the uneasy relationship between general relativity and quantum mechanics. General relativity describes gravity through space-time geometry. Matter and energy affect that geometry, and the geometry influences how matter moves. Space and time are therefore dynamic. They can stretch, curve, and change. Quantum mechanics, meanwhile, describes matter and other physical systems using quantum states, probabilities, superpositions, and entanglement. Both theories are extraordinarily successful in the domains where they have been tested, but combining them completely remains one of the major unresolved problems in theoretical physics. When gravity becomes important at extremely small scales or under extreme conditions, we expect that a deeper framework will be needed. One possible lesson from this problem is that space-time should itself be quantized in some direct way. Another possibility is that space-time is not fundamental enough to quantize in the first place. Perhaps it emerges from a deeper quantum description, much as fluid behavior emerges from molecules. In several research programs, patterns of entanglement appear closely related to geometric structure. The exact details depend on the theory, and there is no single experimentally confirmed picture that everyone accepts, but the general direction is striking. Quantum relationships may contain enough structure for something resembling distance, connectivity, and geometry to arise when viewed at the right scale. Imagine a collection of fundamental quantum systems with no ordinary picture of space assigned to them at the beginning. Instead of saying that one system sits 2 meters from another, we describe how strongly they are related, how information can be shared between them, and how their quantum states are connected. Certain patterns of relationships might then behave as though the systems occupy neighbouring regions of space. Other patterns might behave as though they are far apart. From this perspective, distance would not necessarily be a primitive fact. It could be an effective way of describing the organisation of deeper quantum connections. A rough analogy can be found in social networks, although the physics is far more precise and the comparison should not be pushed too far. Two people can be close in a network even if they live on opposite sides of the world because they interact frequently and share many connections. Two neighbours can be distant in the network because they never communicate. The network has its own kind of structure that does not depend directly on geographical distance. Now imagine the opposite situation, where a deeper network is so fundamental that what we call geographical distance emerges from its pattern of connections. The comparison is not a theory of quantum gravity, but it helps loosen the assumption that distance must always exist before relationships can be defined. If geometry can emerge from relationships, then spacetime may not be a container holding the quantum world. The quantum relationships may be what give rise to the container. This reverses our usual mental picture. We normally imagine particles located inside space, evolving through time, interacting when they come close enough. The emergent view suggests that the deeper theory may begin with interactions, correlations, or information, and only later produce the concepts of location and duration that make the large-scale world look familiar. Causality becomes especially interesting at this point, because causal structure depends on which events can influence which others. In relativity, space-time does more than tell us where things are. It places limits on possible influence. Some events can be connected by signals, others cannot. The geometry separates what can lie in the causal future of an event from what cannot be reached by any ordinary physical influence. If that geometry emerges, then the boundaries of causal influence may emerge as well. The rule that causes must lie in particular relationships to effects might become a property of the large-scale space-time rather than an instruction written into the deepest layer of physics. This would help explain why causality is so reliable without requiring it to be fundamental. Once a smooth space-time appears, causal order can become extremely stable. Light and matter follow the effective geometry. Signals have well-defined limitations. Macroscopic events leave records. Thermodynamic processes establish a temporal direction. Everything combines to produce the ordinary causal world. At the deeper level, however, the building blocks might not come labelled as cause, effect, before, after, here, and there. Those labels could become meaningful only after the underlying structure settles into something resembling space-time. There is a fascinating possibility hidden inside this picture. If space-time emerges from quantum relationships, then changing those relationships may correspond to changing geometry. In some theoretical work, researchers have found strong mathematical links between patterns of entanglement and features that resemble spatial connectivity. Reduce certain connections and regions can behave as though they move farther apart. Strengthen the appropriate relationships and the effective geometry can become more connected. Again, this does not mean physicists can sit in a laboratory and move cities closer together by adjusting a few entangled particles. These ideas belong to highly idealized theoretical settings. Their importance is conceptual. They show that geometry and quantum information may be more closely related than the old picture of particles sitting inside a fixed container suggests. Once space-time becomes an emergent object, the familiar question of what happened first can lose some of its authority. Before and after are temporal concepts. If time itself appears only at a higher level, then demanding a definite temporal order at the deepest level may be like demanding that an individual molecule possess the temperature of an entire room. The question could be meaningful only after enough fundamental structure exists for time to emerge. This does not prove that fundamental reality is timeless, but it makes the possibility scientifically reasonable. Some approaches to quantum gravity do indeed encounter descriptions in which ordinary time becomes difficult to identify. The equations or underlying structures may not contain a preferred universal time variable, playing the role we expect. Instead, time may arise through relationships between parts of the system. One subsystem can function as a clock relative to another. Change becomes something measured internally rather than against an external cosmic stopwatch. This fits naturally with a broader lesson of relativity, where there is already no single universal time shared by the entire universe. The idea of relational time also changes how we think about causation. In ordinary reasoning, a cause acts, and then the effect appears later. But if time itself is defined through relationships between physical systems, then the causal sequence may depend on those relationships rather than existing independently of them. There may be no external clock standing outside the universe to declare that one fundamental event definitely happened first. Instead, ordering could emerge along with the physical structures that serve as clocks and records. This is where the block universe becomes useful, because it gives us another way to question the idea that reality is constantly producing the future from the past. In the block universe picture associated with relativity, space-time is treated as a complete four-dimensional structure. Events at different times are represented in the same overall geometry, much as different locations are represented within space. Your childhood, this present moment, and events in your future occupy different positions in space-time. The picture does not require one universal present moment moving forward and bringing new events into existence. Our experience is very different. We feel located in a present that seems to move. Yesterday feels gone. Tomorrow feels unreal. The current moment feels uniquely alive. Yet relativity gives no universal definition of now shared by every observer throughout the cosmos. Two observers moving differently can disagree about which distant events are simultaneous with their present moment. That makes it difficult to treat the present as one objective slice of the universe sweeping forward everywhere at once. The block universe responds by treating the entire space-time history as equally part of the physical description. This does not mean that every event feels present to us. A person located at one region of space-time has access only to information available from that region. Memories, records, light signals, and causal influences still obey the local structure. The block picture concerns what exists in the physical description, not what any observer experiences at one instant. At first, this seems to make causality unnecessary. If the future already exists somewhere in the block, why would the past need to cause it? Why say that one event produces another when both are simply parts of the same structure? But causality does not disappear so easily. The geometry of space-time still distinguishes which events can influence which others. A signal sent from one event can reach some later events, but not arbitrary regions. The structure still contains causal relations. What changes is the mental image of causation as the process by which reality itself manufactures new moments. Think of a long road shown on a complete map. One town lies earlier along your route and another lies later. From the perspective of your journey, you reach the first town before the second. Your decisions in the first town may affect what happens when you reach the second, yet both towns already appear on the map. Travelling from one to the other does not create the second town. The map contains the whole route, while your experience unfolds locally along it. The block universe treats space-time somewhat like that complete map, although time is not identical to an ordinary spatial dimension, and the analogy should remain modest. This creates an interesting distinction between causation and production. Perhaps an earlier event does not literally manufacture a later event into existence. Instead, the two events belong to a larger structure in which one stands in a causal relationship to the other. The earlier event can influence the later event because the laws and geometry connect them in a particular way. From inside the history, the relationship looks exactly like ordinary cause and effect. From the viewpoint of the complete space-time description, both events are parts of the same four-dimensional pattern. The difference is subtle but important for our larger question. We often treat causation as though it must be a fundamental process flowing through time. The block universe suggests that causation might instead be a structural relationship between events. Causes and effects could be arranged within space-time without requiring an additional cosmic process called the flow of causation, moving from one moment to the next. This perspective also makes retrocausal interpretations easier to understand without immediately imagining paradoxes. If the complete space-time history is treated as one structure, then conditions at different temporal boundaries can constrain the same physical process. An earlier preparation and a later measurement may both belong to the full description. We do not have to imagine the future being created first and then sending a message backward. We can instead think of a history, satisfying relationships across space-time as a whole. A simple everyday analogy is a finished maze drawn on paper. The path from entrance to exit has a global structure. If you solve the maze from the entrance, you experience the choices sequentially. You reach a junction, make a decision, and continue. Someone looking at the entire maze from above sees the whole arrangement at once. The exit does not send a signal backward to create the earlier path, but knowing the complete structure changes how the route can be described. A global description and a local sequential experience can both be valid without contradicting each other. The block universe does not solve every problem about time. It raises difficult questions of its own, especially about why we experience a moving present, why we remember the past but not the future, and how probability should be understood if future events are included in the complete structure. Thermodynamics remains important because it gives observers inside space-time an arrow. Our memories point toward lower entropy conditions. Records accumulate in one direction. Biological processes operate irreversibly. Those features can produce the experience of a flowing, causally ordered world, even if the space-time description itself is static in a larger sense. This brings us back to emergence again. The universe may have several layers of description, each with concepts that become natural only at that level. At one level, we have quantum relationships. At another, something resembling space-time geometry may emerge. Once space-time is available, causal structure becomes meaningful. Once large systems interact with environments, decoherence produces stable histories. Once thermodynamic asymmetry becomes strong, a direction between past and future appears. Once organisms evolve inside that environment, memory and prediction reinforce the same direction. By the time a human being asks what caused something, an enormous amount of physical structure is already in place. Seen from this angle, cause and effect begin to look less like the first rule of reality and more like the final product of several layers working together. That does not make causation weak. It makes it impressive. A rule can be emergent and still dominate everything at the scale where it applies. Pressure is emergent, yet it can crush a submarine. Temperature is emergent, yet it can melt metal. Biological life is emergent, yet it can transform a planet. Causality could be emergent and still remain one of the most reliable features of human experience. There is also a deeper possibility. Perhaps even the distinction between objects is partly emergent from the network. We are accustomed to imagining separate things that later form relationships. Quantum theory often suggests the opposite order may be more appropriate. The joint state can be fundamental, while the individuality of the parts becomes meaningful only under certain conditions. If space-time also emerges from relations, then the universe at the deepest level may not resemble a collection of objects moving from cause to effect. It may resemble a structure of constraints and correlations from which objects, locations, times, and causal arrows all appear together. This is difficult to picture because our imagination depends on space. Try to imagine something without location, and the mind immediately puts it somewhere dark and empty, which is still a location. Try to imagine reality without time, and we picture everything frozen in one moment, which still assumes a moment. The concepts we are attempting to remove are the same concepts our imagination uses to build pictures. Mathematics can sometimes go where visualization cannot, but even without equations we can understand the logical possibility. A deeper theory does not have to look like the world it produces. The same is true in familiar physics. A gas does not look like its statistical description. A magnetic field does not look like the equations used to represent it. A quantum state does not look like a tiny physical cloud floating around in ordinary three-dimensional space. Our everyday pictures are tools, not guarantees about the ultimate form of reality. Emergent spacetime asks us to take that lesson seriously. There is no final experimental verdict showing that spacetime definitely emerges from entanglement or from one particular quantum network. Different approaches to quantum gravity offer different possibilities, and translating their mathematical results into statements about physical reality remains difficult. It would be a mistake to present emergent spacetime as an established fact. What matters for our question is that respected physical frameworks allow us to investigate a world in which spacetime is not fundamental, and once that possibility is open, fundamental causality becomes less obvious as well. The block universe has a similar status. Relativity strongly motivates the idea that there is no universal present, but exactly what that means philosophically remains debated. Some interpretations treat the four-dimensional spacetime picture as evidence that past, present, and future are equally real. Others prefer different accounts of temporal existence. Physics constrains the discussion, but it does not settle every philosophical question by itself. What relativity does make difficult is the simple picture of one universal now moving forward through the cosmos at a single rate. Together, emergent spacetime and the block universe attack causality from opposite directions. Emergent spacetime asks whether the arena in which causal order is defined exists fundamentally at all. The block universe asks whether, even once spacetime exists, we should imagine the future being produced moment by moment from the past. One pushes beneath spacetime, while the other looks at spacetime as a complete structure. Both weaken the assumption that reality must fundamentally be a chain of events in which one moment creates the next. And yet, the ordinary causal world remains exactly where we left it. You still cannot receive a message before it is sent. You still cannot remember tomorrow. You still have to place the bread in the toaster before expecting toast. The large-scale structure of space-time, thermodynamics, decoherence, and information makes these sequences stable. The fact that a deeper description might be more relational does not dissolve the effective rules governing everyday events. That distinction is the safest way to approach all of this. Fundamental and real are not the same thing. A cause can be real without being fundamental. Time can be real without being fundamental. Space-time can be real without being fundamental. What matters is the level at which the concept becomes necessary and reliable. At the level of human life, causality is unavoidable. At the level of fundamental physics, the question is still open. We can now see why the original question has become harder than it first appeared. At the beginning, cause and effect seemed like a simple sequence. One event happened and made another happen. Then quantum mechanics showed that physical alternatives need not always possess definite classical histories. Indefinite causal order showed that even the arrangement of operations can resist one fixed sequence. Entanglement gave us relationships without ordinary directional signals. Thermodynamics explained why large systems acquire a strong temporal arrow. Retro-causal ideas showed that some quantum descriptions can treat later conditions as part of the full structure without permitting controllable messages into the past. Emergent spacetime now suggests that the very concepts of before, after, distance, and causal connection may appear only after deeper quantum relationships organize themselves into the world we recognize. At this point, there is one question left that gathers all the others together. When we say that a cause produces an effect, are we describing something the universe fundamentally does? Or are we describing the way a deeper structure looks from inside a macroscopic world with stable space-time, irreversible records, and observers who remember only one temporal direction? The difference is easy to state, and surprisingly difficult to settle, because every experiment we perform is already carried out by large classical observers living inside the causal world we're trying to explain. The final step is therefore not to search for another exotic phenomenon, but to return to the simplest statement we began with and ask whether the word cause is naming a basic ingredient of reality, or a remarkably successful pattern that appears only after the deeper structure has already done most of the work. By now, the original question has changed shape. At the beginning, cause and effect seemed almost too obvious to question. Something happens, then something else happens because of it. Push the cup and it moves. Strike the match and it burns. Press the switch and the light comes on. The world appears full of sequences in which one event produces another, and that pattern is so reliable that we build nearly every practical decision around it. Yet after looking at quantum mechanics, indefinite causal order, entanglement, thermodynamics, retrocausal ideas, and the possibility that spacetime itself may emerge from deeper quantum relationships, the simple picture is no longer quite as simple. The issue is not whether causes and effects exist in everyday life. They clearly do. The harder question is what we mean when we say that the cause produces the effect, and whether that production is a basic feature of reality or a useful way of describing a deeper structure. Take a very ordinary example. You push a glass across a table. Your hand touches the glass, forces act through the contact, the glass accelerates, friction opposes its motion, and eventually it slows down. There is nothing mysterious about describing your push as the cause of the motion. If you had not pushed the glass, everything else being equal, it would not have moved in the same way. You can repeat the experiment. You can change the strength of the push and observe a different result. You can place the glass on another surface and see how friction changes what follows. This is exactly the sort of situation where causal language is most powerful. We can intervene on one part of the system and observe consequences elsewhere. That ability to intervene is one reason causation means more than simple correlation. Two things can vary together without one producing the other. The number of people carrying umbrellas and the amount of rain are correlated, but umbrellas do not normally cause rain. Both are related because rain causes people to carry umbrellas. Similarly, ice cream sales and sunburn might increase during warm weather, but buying ice cream does not cause sunburn. A third condition helps explain both. Causal reasoning tries to distinguish these cases by asking what would happen if we deliberately change one variable while holding relevant background conditions steady. This method works extremely well in the ordinary world. Medicine uses controlled trials to ask whether a treatment actually improves outcomes. Engineers change components to identify what caused a machine to fail. Scientists isolate variables to determine which conditions produce which effects. Everyday life contains informal versions of the same reasoning. You press a button repeatedly and discover that it controls the lamp. You stop watering a plant and observe what happens. You move a noisy object away from the wall and learn why the vibration disappears. Causation becomes closely connected to control, prediction, and intervention. At this level, asking whether causation is fundamental can seem unnecessarily philosophical. If pushing the glass reliably moves it, what more do we need? The answer depends on what kind of explanation we are looking for. If we want to understand the glass, ordinary causality is enough. If we want to understand what the universe is made of at the deepest level, we have to ask whether the same concepts remain necessary when we strip away the large-scale conditions that make everyday causation so clear. That distinction has appeared throughout this journey. A concept can be indispensable at one scale without appearing in the same form at another. Temperature is one of the easiest examples. The temperature of a room is completely real. It can be measured, controlled, and used to predict physical behavior. Yet a single isolated particle does not possess the temperature of the room in the same way. Temperature becomes meaningful through the behavior of enormous numbers of microscopic components. The large-scale concept is not an illusion, it is emergent. Causality may work similarly. The macroscopic world contains stable objects, persistent records, a thermodynamic arrow, decoherence, and a space-time structure that clearly limits possible influence. These ingredients cooperate so effectively that causal chains become nearly unavoidable. One event leaves traces that survive into later states. Information spreads into the environment. Memory records earlier events. Physical signals travel along allowed paths. Large systems remain stable enough that we can identify them before and after interactions. The result is a world where causes and effects can be tracked with remarkable consistency. None of those facts by itself proves that causal production is written into the most basic level of reality. It may instead be something that appears once enough structure is present. The push causes the glass to move because at the scale of hands, glasses, and tables, the universe has already settled into a regime where stable, macroscopic states and directional records exist. The deeper quantum description may contain relationships that do not resemble the simple transfer of influence we imagine when watching the glass. Quantum entanglement made this especially clear. Two systems can display correlations that are physically real, while resisting the picture of one system simply sending an ordinary causal message to the other. The joint relationship matters in a way that cannot always be reduced to separate local properties. Indefinite causal order pushed the idea further. Under suitable quantum conditions, even the order in which operations act can refuse to fit into one fixed classical sequence. Instead of assuming that one operation must secretly have happened first, the process can preserve coherence between different orders. These examples do not tell us that causality disappears. They tell us that the causal structure available in classical physics may not be the only structure nature permits. The deeper theory might contain relationships that become causal only when viewed under macroscopic conditions. If so, asking which event produced which other event at the deepest level could sometimes resemble asking which individual water molecule contains the wave. The question assumes that a large-scale property must have a microscopic owner. There is another possibility. Perhaps causality really is fundamental, but our ordinary version of it is only a simplified form. A deeper causal structure might not require one fixed order. It might allow quantum combinations of possible orders while still preserving restrictions on communication and consistency. What emerges at large scales would then not be causality itself, but a classical version of a more general quantum causal structure. That possibility is important because physics often replaces simple concepts with broader ones rather than eliminating them. Newtonian gravity was not simply declared useless when general relativity arrived. It became an approximation that works extremely well under ordinary conditions. Classical mechanics did not vanish when quantum mechanics appeared. It became the effective description appropriate for large systems and familiar scales. Perhaps classical cause and effect will eventually occupy a similar position. It may turn out to be the ordinary limit of a deeper framework in which causal relationships can be indefinite, relational, or dependent on quantum geometry. At the moment, physics has not settled which of these possibilities is correct. There is no final experiment demonstrating that causality is entirely emergent. There is no universally accepted theory of quantum gravity showing exactly how space-time and causal order arise. There is no agreement that retrocausal interpretations provide the best explanation of quantum correlations. The subject remains open because several of our most successful theories describe different aspects of reality using different structures. Quantum mechanics is extremely successful at describing macroscopic phenomena. General relativity is extremely successful at describing gravity and space-time. Thermodynamics is extremely successful at explaining the large-scale arrow of time. Yet putting all of these into one complete picture is difficult. Causality sits directly in the middle of that problem because it connects time, information, space-time, and physical influence. This may explain why the question feels both scientific and philosophical. Science normally asks what happens under particular conditions and tests the answer through observation. Philosophy often asks what our concepts mean and whether the structure of our explanations reflects reality itself. Causality belongs to both conversations. We can test causal relationships in laboratories, but when we ask whether causation is fundamental, we're also asking what kind of thing a causal relationship actually is. One possibility is that causation is a pattern in the laws. An earlier state and a later state are related according to physical rules, and we call that relationship causal because changing the earlier conditions changes what follows. In this view, the There does not need to be a separate substance called causation flowing between events. The laws and boundary conditions are enough. Another possibility is that causation is closely connected to information. A cause is something whose information can propagate into later systems. Strike a bell and information about the strike spreads through vibrations and sound. Push a glass, and information about the push appears in the motion of the glass, the table, the air, and the surrounding environment. Later states contain traces of earlier ones. Causal influence becomes connected to the direction in which physical information can be transmitted and recorded. A third possibility is that causation is primarily structural. Events stand in relationships within spacetime, and those relationships determine which events can influence others. From this perspective, saying that one event causes another may be less about a mysterious production process and more about where the two events sit inside the physical structure of the universe. The block universe makes this especially interesting. If the entire space-time history is represented as one four-dimensional structure, the future does not need to be imagined as something physically generated by the past moment by moment. Earlier and later events are both parts of the full geometry, yet causal relationships still distinguish which events can influence which others. A star can emit light that later reaches a planet. A person can make a decision that changes what happens at a later location along their history. Nothing about the block picture removes those relationships. What it questions is the idea that causation must be understood as reality manufacturing new moments from old ones. This difference between relationship and production may be the key to the whole subject. When we say the push produces the movement, perhaps we're adding a mental picture to a physical relationship. The physical theory tells us how states are connected. It tells us what changes when conditions change. It tells us which signals can reach which places. It tells us which outcomes are probable. The feeling that something literally flows from cause into effect may come from the way human beings experience sequences. Our experience is strongly directional. We remember earlier events and not later ones. We act in the present and observe consequences afterward. Our bodies depend on processes that increase entropy. Our brains form records in one temporal direction. We evolve to predict what comes next by using information about what came before. A creature that could not learn causal patterns would struggle to survive in an environment where those patterns are reliable. Because our entire cognitive life is built inside that direction, causation feels active. The past seems to push the future forward, but perhaps the universe itself does not experience events that way. The idea that reality flows may belong to observers embedded inside thermodynamic time, rather than to the deepest physical description. This does not make human experience wrong. A map and a journey describe the same landscape differently. The complete map contains the entire route, while the traveller experiences one location after another. Neither description cancels the other. In a similar way, a global physical structure could contain an entire set of relationships, while observers inside that structure experience causes followed by effects. There is also a practical reason not to worry that fundamental causality might disappear. Emergent rules can be extraordinarily reliable. Nobody refuses to use temperature because it is emergent. Nobody worries that a bridge will forget how stress works, because atoms follow quantum mechanics. The large-scale laws are stable precisely because they arise from enormous numbers of microscopic interactions. Once a system enters the right regime, departures from the effective behaviour become fantastically unlikely. Causality may enjoy the same protection. By the time we reach the scale of people, planets, machines and stars, quantum coherence between alternative causal orders is generally lost to the environment. Spacetime behaves smoothly. Thermodynamic records point consistently in one direction. Signals obey relativistic limits. The causal world is not fragile. It is reinforced by nearly everything about the conditions in which macroscopic observers exist. This explains why the strange quantum exceptions do not appear in ordinary life. You do not need to wonder whether switching on a lamp and seeing the light occur in an indefinite order. The apparatus is large, warm, and interacting with its environment. Countless records distinguish the sequence. The causal order is effectively fixed long before your brain becomes aware of it. Whatever deeper quantum possibilities exist, they have already been converted into an ordinary classical history. The interesting question is how far downward we can trace that history before the concept begins to lose its familiar form. At some point, stable objects become quantum states. Definite trajectories become alternatives. Independent properties become entangled relationships. Fixed operation orders can become indefinite. Spacetime itself may need a quantum description. Somewhere across those transitions, the causal world we know either emerges or changes into something more general. Perhaps one day, a successful theory of quantum gravity will make this transition precise. It might show how a network of quantum relationships produces geometry, time, and definite causal structure. It might reveal that causal order was present in a deeper form all along. It might show that what we currently call spacetime and causality are two aspects of the same emergent phenomenon. Or it may force us to replace the entire question with concepts we do not yet have. Physics has done that before. People once asked what medium carried light through empty space because waves were expected to need a material medium. The question seemed unavoidable until the underlying theory changed. People once treated space and time as separate universal backgrounds until relativity combined them into spacetime and made their measurements dependent on motion and gravity. Perhaps asking what causes an effect at the deepest level will eventually turn out to contain assumptions that a future theory no longer needs. For now, the most honest answer is that causes certainly produce effects in the world where we live, provided we use the word produce in the practical scientific sense. Intervene on the cause and the probability or behaviour of the effect changes. Physical influence passes through allowed channels. Records preserve the relationship. Predictions succeed. Medicine, engineering, and ordinary life depend on it. At the fundamental level, the word produce becomes harder to define. Quantum correlations can exist without ordinary signals. Causal order can become indefinite. Time may not possess one universal sequence. Later conditions may appear symmetrically in some interpretations. Space-time itself may emerge from a deeper structure. These facts leave open the possibility that cause and effect are not primitive ingredients, but features of a larger pattern. There is something strangely reassuring about that possibility. We began by questioning one of the most dependable rules in daily life, yet nothing important about daily life needed to be abandoned. The kettle still boils after you switch it on. The rain still makes the pavement wet. The alarm still causes an immediate desire to ignore the alarm. What changes is not the reliability of these experiences, but the depth of the explanation beneath them. The universe often works this way. The closer we look, the more familiar things turn out to be collective effects of unfamiliar structures. Solidity comes from quantum interactions. Colour comes from light and perception. Temperature comes from statistical behaviour. Gravity becomes geometry. Space and time become relative. The surprise is not that ordinary reality is false. The surprise is how much deeper structure is required to make ordinary reality possible. Causality may join that list. The clear chain from cause to effect may be what reality looks like after quantum possibilities have decohered, after records have formed, after entropy has established a direction, and after space-time has become sufficiently stable to define which events can influence which others. Beneath that level, there may be correlations, constraints, quantum processes, and structures for which asking what came first is not always the most useful question. And perhaps that is the point worth carrying away tonight. Cause and effect may not need to sit at the bottom of reality in order to matter. They may be something the universe builds. Once built, they become stable enough for stars to evolve, chemistry to proceed, organisms to learn, memories to form, and people to sit somewhere late in the evening wondering whether causes really cause anything at all. You've been part of a causal chain while listening to this entire journey. Sounds reached your ears. Signals moved through your nervous system, memories formed. Perhaps one idea changed how you think about another. Somewhere along the way, the question that began as a simple challenge to cause and effect became a question about time, information, spacetime, and the structure of reality itself. And now, as we reach the end of this particular journey, let me return to something much simpler. Where are you listening from tonight, and what series of causes, choices, accidents, recommendations, habits, and curious little decisions brought you here? Perhaps there is a clear answer. Perhaps there are dozens. Perhaps tracing the chain far enough would eventually become impossible, because every cause depends on earlier conditions, and those conditions depend on others before them. That is another curious feature of causal explanation. We can always ask what caused the cause. Push the question far enough and eventually we reach the edge of what our current theories can explain. Cosmology asks about the earliest conditions of the universe. Quantum gravity asks what exists beneath space-time. Fundamental physics asks whether the structures we use to explain reality are themselves things that need explanation. Cause and effect may therefore be less like the bottom of the ladder and more like one of the strongest rungs. It supports almost everything we do, even if something deeper supports it in turn. If you found this slow exploration interesting, calming, or useful company, while the day becomes a little quieter, you are very welcome to like the video and subscribe. It helps this small corner of physics reach other people who might enjoy spending an evening questioning something they had previously considered obvious. For now, though, there is no need to solve causality before going to sleep. The universe has been managing its relationships for a very long time without requiring us to settle the terminology. The large-scale world will continue behaving causally by morning. Your clock will move forward, light will arrive after it is emitted. Breakfast will still require preparation before eating, unless someone else is kind enough to prepare it first. Whatever exists beneath that familiar order can remain there for tonight. Maybe causes truly produce effects. Maybe they are connected parts of a larger space-time structure. Maybe both emerge together from quantum relationships that do not resemble either one. Physics has not finished answering that question, which is probably appropriate. The deepest questions rarely become less interesting simply because we give them a name. So let the question remain open. Let the causes and effects of the day settle into memories. Let the room continue exchanging its quiet signals. And let the ordinary arrow of time carry everything forward in the direction it has always seemed to go. Whether that arrow is fundamental or something the universe creates along the way, from where we are now it still points toward the same immediate consequence. Rest.